Hello, good morning to everybody, and thanks for joining this DYNAeLAST expert talk. Well, I'm going to present myself. My name is José Javier Egurrola, and I am the technical manager of the polymer side of ELASTOMERS. And together with me, there is Aiseti. Hi, Aiseti.
Hello.
Can you present yourself?
Okay, so my name is Aiseti. I am a researcher here in ELASTOMERS, and well, my research activity is mainly focused to understand the dynamic mechanical behavior of elastomeric materials, not only for characterization but also for modeling, in order to be able to predict the thermomechanical behavior by means of finite element analysis.
Okay, so we are in the third day of the DYNAeLAST program. Well, remember that during the last 2 days, we have organized, together with MetraVip, a specific training session related to elastomers and dynamic properties. It has been a nice experience, and the companies that have attended this training session have had the opportunity to learn about the theory that is behind the dynamic properties of elastomers, going deeper in the modelization of these properties, and also a practical session with their own materials in our MetraVip DMA machine. While you are now watching a video related with the workshop, with the training session, sorry. And well, Aiseti, could you make a small summary of the different points that you have seen in the training session?
Yeah, sure. So as José Javier Egurrola has also explained, so DYNAeLAST event, the course, and also this expert talks for us is a networking opportunity. And also during the course, we have been involved different people for more industrial companies, more research-related companies. And the main was to give not only theoretical course, but also a practical course to see the potential of the dynamic mechanical analysis. How can we use the DMA to not only to understand the basics of the elastomeric materials, viscoelasticity and their behavior, but also to apply the dynamic mechanical analysis and the different tests that we can perform in order to model their behavior, to get material models that are able to predict the performances that we can have in products that are going to be in mainly cyclic loading conditions. So we have covered different topics from very basics of the DMA and the viscoelasticity of elastomeric materials up to more specialized topics related, for example, with the high frequency related testing capabilities that we can perform with MetraVip's DMA machines. So because in this kind of machines, we can perform not only via experimental way, determine up to 1 kilohertz viscoelastic properties characterization, but also we have also shared other modeling strategies in order to be able to go even to higher frequency ranges. We have also had a specific topic related with applying the DMA to be able to model or to get material models that are able to predict all the nonlinear behavior that these kind of materials and products can have. For example, what happens if our product is going to suffer different frequency ranges. For example, we know that in the new hybrid electric vehicles, high frequency requirements are going to be key in terms of structural dampening, but also in terms of NVH. So how can we apply DMA to model and to capture this high frequency, or for example, other cyclic loading conditions? So the aim at the end was to go more in deep and to see the potential and how our partners and that are involved in the elastomeric materials and the transport industry can apply all these capabilities of DMA.
Okay, so well, the idea is that the next year we want to organize a new edition of this training course, more or less in the similar field, but of course adding the new developments that we can do during this year. So now let's talk about the expert talks that we have today. As we have explained in different communication, we want that DYNAeLAST will be a networking space for those people that have a special interest in elastomers and dynamic properties, scientists, professionals, technicians, and even end user. And this year we have maintained the online version of the workshop of the expert talks, but well, the idea is that we expect that in the next year it will become a presential meeting during the next years. Okay, so while DYNAeLAST it's completely in line with the specialization of LeArticle, that it's focused in the modeling of polymeric materials for sustainable transports, and the main project that we are running here in LeArticle have the objective to understand the rheological and the mechanical behavior of polymeric materials, modeling this behavior for a better design of new products. Because of that, we have in this workshop the whole value chain from the end users like CAF, that it's always suffering dynamic modeling for the construction of the entire train, the material supplier like ABN in charge of developing new materials that fulfill those requirements. Of course, Metrabit, researching and developing characterization methodology for testing those properties, and a software developer like Endurica that after modeling the behavior, well, they are able also to develop a software to simulate the fatigue behavior. And of course, LeArticle supporting all the value chains with intensive research in material characterization, modeling and digitalization, and following our mission that it's transfer this knowledge to the industry. So this is our main point in our mission: try to make research, of course, and then try to transfer this knowledge to the industry. Well, just a reminder: you can write all the questions in the chat. You have to register you have to just log you with your email in the YouTube channel, and then you can make the questions, and then Iseti and me will make the questions after the different talks. Of course, between the speakers also the same. You can just raise your hand and you can make questions one to each other. Okay. So well, I think that we can already start with the first talk. So to begin with the workshop, we have with us Joseba Murua from CAF. Joseba Murua is a vehicle dynamic engineer with industrial and academic experience in railway and aeronautical sector. He holds a mechanical engineering degree from Technion, as well as a master and PhD degrees in fluid structure interaction from the Imperial College in London. He has worked in mathematical modeling and numerical simulation of the multi-body systems, aerodynamics and elasticity, and he also has experience in physical testing, both on tracks and in air. Currently, he leads the dynamic and rolling team in the research and development department of CAF, where he suffers but also enjoys the capriciousness of rubber and its impact on the train behavior. So, Joseba, welcome, and it's your turn.
Right. Can you hear me?
Yeah. Perfect.
Yeah, you can hear me. The screen. All right, so do you see my screen as well, the presentation mode? Can you see my screen? Okay, yes, thanks. Okay. All right, so first of all, good morning, everyone. Thank you for For the introduction, thanks to Leartiker for inviting me to be a speaker. It's an honor and a privilege to be here. I must confess that I feel a bit of an imposter syndrome, considering my distinguished co-speakers and the knowledgeable audience, but I'll try to give you an overview of how we suffer rubber in CAF. Okay, so CAF at heart is a rolling stock manufacturer. I will give a brief sort of an overview of what the company does. We do more things, but at heart we are a rolling stock manufacturer, a train manufacturer. We came to the field of rubbers relatively late and as non-experts, and the last few years it's been a really a steep learning curve for us. So essentially we did have a lot of rubber components in our trains, but we didn't know much about how rubber behaved. So we started having problems, particularly as we started being awarded more contract and maintenance contracts, and with these maintenance contracts we've realized how rubber is a very, very particular material and it needs to be dealt with. So in that journey, in that very steep learning curve, we've had the help of different institutions that I'd like to acknowledge before starting the presentation. First of all, Leartiker, who really, they are our neighbors. They are geographically close by and they've been a tremendous help to us. ITA, a technological center in Zaragoza, who have also helped us a lot in this learning curve. And I'd also like to thank Metallo Caucho, MPC, which is one of our main suppliers of rubber components, and they suffer with us many of the problems we experience. So also some of the material I will be presenting here has been undertaken in collaboration with them, with Leartiker, ITA and Metallo. So I give credit to them, particularly the technical work, the heavy lifting, and the theoretical knowledge lies on them. I am just the funding partner, essentially, of this collaboration. So as an outline, I'd like to start briefly introducing CAF for those of you who might not know the company. Like I said, we are at heart a train manufacturer. We have a lot of rubber parts in our suspensions, and the variability of rubber during service plays a major role on our design and essentially on safety. So it also affects other parts of the train behavior, but particularly safety is the most critical aspect, and the changes that the rubber experiences in service are critical to that. So with this first background presentation, then I'd like to give an overview of a couple of application examples. They will necessarily need to be relatively high-level descriptions of these projects because of intellectual property issues on the one hand, and on the other because of time limitations as well. But this would be, I hope it is of interest to you. So, history of CAF, don't worry, I won't go through all the details, just a couple of highlights of milestones. CAF originally was an ironworks company in 1892, and 1917 is considered our official founding date. This is when we actually started building train material. Here, from 1917 to the early 90s, really nothing important seems to have happened because we essentially sold in the national market within Spain, and it wasn't a very international company or diversified. But in the early 90s, after a strong and painful crisis in the state, CAF needed to diversify and to internationalize. So there was a shareholder consolidation process, and since then we've gone through a very quick growth, sometimes very inorganic, and now on top of doing trains as our original goal was, now we do everything. We do a lot of things. We do buses, we do even financial services, we do infrastructure, we do signaling, and we are involved in a lot of different areas. So We, as product and services, like I said, railway vehicles are still at our core product, and we have high-speed trains, regional and commuter trains, metros, tramways, and even locomotives. But since a few years ago, when we bought Solaris, an electric bus company in Poland, the European leader, we also do buses. We also offer services, like I said, even financial services. We do signaling, which is a big thing in railway. We do all sorts of components. And the big thing right now is the integrated transport systems. So as our slogan shows, we say your way to future mobility. We don't want to be just a manufacturer of a transport system, but we want to give you a mobility solution from A to B, an integral solution. It can be a bimodal or trimodal, multimodal transportation that combines a train, a bus, and a taxi. And we want to have the capability to develop the infrastructure for that. So there are a number of companies that make up the CAP group. Particularly, I am on the Research and Development Department, which is I+D for its Spanish acronym. Like I said, we have a very strong international presence at the moment with manufacturing and maintenance centers all over the world and projects in all continents as well. So, a brief introduction to the train suspension and running dynamics. The bogie is essentially the chassis on the train. This is what supports the car body, okay, and makes the link to the track. There are usually two suspension stages on a train. The secondary suspension, which links the car body to the bogie frame, and the primary suspension, which links the bogie frame to the track. Usually in a train, wheels are metallic, so they don't offer a suspension characteristic, although we do have elastic wheels as well. This is a 3D view of a bogie, where we can see the wheels with the axle that links them. The primary suspension is here in the axle box, linking it to the bogie frame, and then the secondary suspension, in this case made out of air springs, where the car body would sit. So just another view of the bogie with different elements. I just want to highlight the primary suspension in the axle box because it's one of the key components. Regarding safety, it's probably the most important component on a train, and the primary suspension is very often made out of rubber. In particular, we have different types of solutions depending on the vehicle. A very common one, and I will be talking about this later on, is rubber springs or meta cones, which are rubber metal parts. Like you can see here, this is an emergency spring of the secondary suspension, which has conceptually is very similar to the primary suspension. Also in the secondary suspension, we usually have air springs, which are filled with air, but are made out of rubber. Other rubber elements on the bogie, a very frequent one are the bushings. So we have a lot of articulations, and most of these articulations have rubber components there. It tends to be a problematic part because of very limited space and very high loads. Tends to fail, and bump stops, which are very critical also to ensure that we are within the envelope of the train when it comes to gauging, that it doesn't exceed the maximum displacements. So these are also critical elements. These ones in particular, sometimes from a safety point of view as well, they might be crucial. Crash course on running dynamics. When we design a train, we need to ensure that it is safe, that it's comfortable, and that we minimize the life cycle costs because of the damage to the track. To do that, in the design phase, we use multi-body dynamic simulations. We do a multi-body dynamics approach. We essentially represent our train as a system of masses and inertias linked through springs and dashpots, and also friction elements, as well shown here, KY and KX. A big part of the multi-body dynamics is the wheel-rail interaction modeling. Here, just an illustration of how we contact calculations between the wheel and the rail. This is numerically very complicated, let's say. it gives lots of problems when it comes to convergence, and it is quite intensive computationally. So this actually usually defines the computational effort required. But mostly because of that, we cannot really use very sophisticated rubber models in routine multibody dynamics calculations. So in the context of a European project, DYNAtrain, different rubber model options were used for train suspensions. So different Kelvin-Voigt, thinner, different combinations, more or less fewer elements. Lots of them were analyzed. We also, at in-house, we developed our own model, a Berg model it's called, and we got very good agreement for various challenging calculation scenarios. So we compared testing to simulations, and we got very good agreement. So it can be done, for sure, it can be done. But when it comes to, so when it comes to actual multibody simulations, we really need to use simplified rubber models, like I said. So essentially, we use hyperelastic model where we use a nonlinear force deformation curve, but that's about it. Usually, we also have a dashpot in parallel, but this is not even modeling the viscoelasticity in detail. It's usually just a constant value proportional to the critical damping, and that's about it. To be fair, when it comes to the objectives of our simulation, this is enough. There might be some scenarios in which we don't have required accuracy, but in general, it is enough to comply with all the standards and to make sure that we have safe trains. So in our suspension design, we have conflicting design goals, like everyone else, of course. But just wanted to give you a quick rundown of them. Safety against derailment, like I said, this is the first goal. The rest of the goals are secondary. You need to ensure that your train is safe. Our train, a critical scenario for our train, it's this curve simulation in which our train enters a curve, goes through the curve, and then goes through the exit transition. And in the exit transition, in the runoff, it finds an irregularity or a track defect. Okay, so this defines a critical condition where the lateral load experienced by the wheel is maximum and the vertical load experienced by the wheel is minimum. And Nadal formula, the so-called Nadal formula, defines the derailment coefficient as y/q, and it defines an upper limit for this value. If you exceed that upper value, it means that your wheel is gonna climb and it's going to derail. So that's our most critical scenario. This requires usually low stiffness in our primary suspension because what you want is your train to adapt as much as possible to the track. But then, of course, you have other design goals that conflict with the first one. When it comes to gauging, for example, you cannot allow the deformations of your train to exceed the envelope. So you want a stiffness that is high enough. When it comes to stability, the wheel set of a train is by design is inherently it can lead to a hunting oscillation because this is an unstable motion where your wheel set undergoes lateral and yaw motion. There is a speed beyond which it becomes unstable, so you need to ensure that you don't exceed that speed or that your K is high enough to prevent this from happening. When it comes to comfort, here you can have different circumstances, but for example, in this particular case where we tested different bushes of different stiffnesses, this is vertical acceleration experienced by the passenger. We see that a stiffer suspension, stiffer bush leads to higher acceleration, which is less comfortable. So in this particular case, we needed to use the stiffer suspension, but it was a trade-off because we were aware that we were worsening the comfort characteristics. Then there are considerations of tribology and wear, because obviously the train creates damage on the track. These are examples of spalling caused by rolling contact fatigue, corrugation on the track. The wheel itself also wears and loses material, so we want to minimize this. in most cases, or in many cases at least, you would want a relatively low stiffness to delay this as much as possible. And then I wanted to reflect on this final design. It's not really a design goal, but it's more a design restriction, which is space. We can account for this, and we can create a very complete and detailed technical spec, but then in practice, we have very limited space to obtain what we want. So this is a problem usually for our manufacturers, for our suppliers, because we are requesting something that is essentially impossible to manufacture and within the limited space. If we gave them more space, probably they could have more rubber, they could play around with the rubber mix and get something that works. But the problem is that sometimes we just don't have space in the body, and that's something we have to deal with. So this is a bit of context, more context regarding service life, which obviously rubber is a light material. Everyone here knows that, so this doesn't come as a surprise, but it really affects the safety of the train. When we manufacture a train, usually the life expectancy is of 30 years, which is a very long lifespan. And it can even be more, because sometimes after circulating for 30 years in Europe, for example, it can be taken to a developing country to extend its lifespan. For rubber, we usually consider 8 years of lifespan, but during those years, the operating conditions change significantly. On the one hand, you have let's say, external conditions to the rubber itself, like wheel rail wear that I mentioned earlier, or other suspension elements failing or aging, like dampers, for example. This means that the rubber might need to absorb higher deformations or higher loads that it was originally designed for. And then, of course, we have the unpredictability inherent to the rubber. We have, on the one hand, wear and tear. Well, just for the purists, I've used a classification here that it's useful for us, for CAF. We are not rubber experts, so perhaps there might be some disagreement of how I classify this, but it is just something that is useful for us, okay? So fatigue, well known. I'm sure that Wilmars will tell us a lot more about fatigue, so I won't talk about what I don't know, but essentially this is a test we have about an anti-roll system articulation bushing, where we see how the stiffness varies as a function of the cycles that are being applied. So there is a drop in stiffness. Usually in this range we don't have a functional problem, but it might become a problem beyond that. We also have creep, particularly in the primary suspension. This can be very critical. The primary suspension settles, so this is a test according to the standard, where we see the evolution of the settling of the creep, and then this is the prediction for 10 years of lifespan. We've had cases in which the creep was excessive. You consume the travel allowed for the suspension, and you might end up having problems with metal-to-metal contacts. If you don't have enough travel distance for your rubber suspension, you get to metal-to-metal contact, and that can be extremely dangerous from a safety point of view. And then we have a couple of other effects, oxidative aging, and then what I call load-induced stiffening. This load-induced stiffening is specific to the rubber springs, and where I've asked about it and I talked about it, some people find it a bit surprising. So I'll try to explain what it is about. The name, I don't really know another name, so that's why I call it load-induced stiffening. And what it refers to is that if we do, this is a force deformation curve of a quasi-static test of a primary suspension. The blue curve corresponds to the new element, to the new part, and then we apply cyclic loading. Both dynamic creep and fatigue tests are cyclic loading tests, and what we see is that the element stiffens. Then we put it into an oven and it stiffens further. So this last part is what everyone, I guess, is familiar with. This stiffening due to cyclic loading is what it's something seems to be very specific to the primary suspension. We guess it's related to the creeping of the suspension. To be honest, we don't really understand what's going on in the phenomenon, so we just, I will show you an example of what we are trying to do to improve our understanding of it. Dynamic stiffening, I won't talk much about it. This is particularly you've been in the course, I'm sure that you know all this. There is a high dependence on amplitude and frequency. In particular, if we look at this variation of the vertical stiffness, we see that the stiffening can be of more than 40%. That's from a safety point of view, this is tremendous because the derailment coefficient I showed you earlier would increase dramatically with such a stiffening. Okay, so it is critical for us. Loading conditions also play a major role. So if we look at these quasi-static curves overlapping with the static ones, and we draw the tangent, which is essentially the value we use when evaluating our safety, what we see is that if we go from a L node, it corresponds to third condition, no passengers whatsoever, and we move to EL7, which is 7 passengers per square meter, the slope of the tangents has changed significantly. So it is a lot stiffer in this particular case. So if we look at some bar chart, what we see is how from EL node, as we increase the number of passengers, the stiffness increases a lot. From a safety point of view, third condition tends to be the most critical because it's the lowest load on the train, on the wheels, but because the stiffness increases so dramatically depending on the preload, this could become the most dangerous condition. And also I wanted to make a mention of environmental conditions. Obviously rubber is subjected to different environmental conditions. We have projects in which it is very cold, in which it is very hot. We have sandy environments like Saudi Arabia, and we have very corrosive environments in coastal areas with a lot of salt and with or snowy conditions where they put a lot of salt. We've experienced problems of adhesion loss between rubber and metal in these very corrosive environments. Thankfully, our supplier Metallocaucho has found a solution for this, and now we do have a solution, but this is the type of problems we experienced in the past. So just to give you a couple of application examples of projects we are undergoing, like I said, we have this problem with the load-induced stiffening in the primary metacons. So I'll try to give a high-level presentation of this. This project really was undertaken by ITA. They were the ones that carried out the work, and Metallo provided the material. So just as a reminder, I'm talking about this element, primary spring, rubber metal component that is in the primary suspension joining the wheelset to the body frame. This suspension undergoes creep and it undergoes oxidative aging during its lifetime, but it also experiences this load-induced stiffening. So just to evidence this, I have these force deformation curves of elements that were new. This would be the new curve, nominal new state. And then we have curves for parts that are 10 years old. Some of them have been in a warehouse and some of them have been in service. So the ones in the warehouse are here, they stiffen. That's something to be expected because time goes by, but they are still within tolerances actually. But if you look at the ones that have been under cyclic loading, have been in operation, they've stiffened a lot more. They even go beyond the tolerances. I mean, this is not a problem. They were out of service because it's 10 years after manufacturing date, so they have to be out of service already. But this shows how this stiffening effect, it's actually something we see, we observe. If we look at a fatigue test of a different element, we see how the stiffness increases as the number of cycles increases, and we see how the creep also increases. The primary settles further and further. So we think it's related to, it's a combined effect, and we need to deal with it. We need to limit the total stiffening to a 30% maximum because otherwise we will have a massive risk of derailment. And this, of course, constrains the design. So we started, the project is in its infancy. We've done the first steps of trying to predict this stiffening of a primary spring. So this is a sort of diagram. Like I said, it has to be high level. It is in its infancy. Watch this space, and hopefully in the near future we will have some publications explaining the methodology in detail. Essentially, we have the loading history that our part undergoes. We need to convert this to an equivalent load for a specimen for which we are able to predict the evolution under this loading. For the evolution, we use the C1 knot of a neo-Hookean hyperelastic material, and we track its evolution. If we are able to predict how C1 knot is going to evolve for a given cyclic loading, we can determine the stiffness per layer of rubber in between metal sheets. With that, we can calculate the stiffness, and then it's a series association to get the global stiffness. So the stiffness evolution of the specimen, we use a quadruple shear specimen. Like I said, the model of the material is actually rather complicated. I won't go into the details because I don't understand them, but we have an elastoplastic branch, we have a viscoelastic branch, but we only take into account the evolution of C1 knot in the hyperelastic branch. Okay, so we can track it as a function of the cycles being applied. It changes on the amplitude of the cycles and on the preload that is the element is subjected to. To determine the equivalence for the specimen, what we do is we ensure we take into account the stresses on each of the layers of our element, and we replicate those in our specimen, and then that's how we have our equivalence. We have our diagrams to be able to apply the correct loading to the specimen. And finally, like I said, once we can predict the evolution of C1 knot, we can, through finite elements or whatever, we can have the stiffness for each of the layers. We can combine them to get the metacon stiffness. So I would say I didn't give you too much because I cannot at the moment. I think it's a very promising area of research. It is quite fascinating, but we have still some way to go to be able to refine the whole methodology. An example, anti-roll system, fatigue testing. So I gave you an example of something more numerical, and now I wanted to give you a test of a real component. In this particular project, we've worked with both Leartiker and ITA. We have two different experimental setups. I'll give you the details now, and also Metallocoach has provided the material and the components for the testing. So again, as a reminder, we have our anti-roll system on the train. There are bushings on the articulations, rubber bushings, and those are the ones that we are trying to analyze. Why? Because we've seen cracks. Cracks have appeared in some of the projects. These cracks are not a functional problem. We haven't really experienced any safety issues, but if a customer sees them, usually they don't like seeing cracks and they ask for a solution. So we had to deal with it. So a couple of pictures of the failure mode that we've observed. To be honest, this is not very common. It occurs on very extreme conditions, usually a combination of all of these. So you have poorly maintained tracks, a lot of irregularities, very hard on the train and on the suspension, inordinate number of passengers. That's also very important because we are talking about 10 plus passengers per square meter. My first question was, how do you fit more than 10 people in a square meter? But apparently in some projects, that's something that does occur. There are projects in which the track is very, very stringent for the suspension. So we have track twists that are very high, and we have very narrow curves. And also they tend to be corrosive environmental conditions, so particularly in coastal areas. So it doesn't happen often, but when it happens, it is because of a combination of all this. To be honest, we can't really design for this, but the poor maintenance of the tracks is usually beyond what we can do. So we need to deal with it when we have the problem. Like I said, originally we didn't really pay much attention to these elements. They are not safety critical. But as we started having problems and customers complaining, we needed to pay more attention to them. So we tried to understand the problem. It is a multi-axial loading scenario where we have very high radial loads, very high angles, both in torsion and in conic or cardanic axis. And what we saw is that the peak values of all three of them occur at the same position. So this is in the entrance transition to a curve where you have maximum track twist and maximum minimum curve radius. there is a peak where the loads lead to the maximum value. Maximum stress is very, very critical for the element. We try to reproduce real-life failure in a test environment, also because we wanted to test possible solutions. Like I said, we worked with ETA and LeArtiker. It proved a very, very painful experience for us and for them. I'm sure they would concur. Eventually, we ended up with a solution, which is the good thing, but we really were not aware of how difficult this was going to be. We have very high actuation requirements because of the high loads and angles. We have to replicate the in-service loading conditions with the simultaneity and the independence of each axis. And we even experienced failure in other parts of the chain, like breaking the metal, because we were not reproducing exactly what the real-life conditions. Like I said, a very painful experience, but in the end successful. So just the video, this is LeArtiker, the test bench on LeArtiker, so that you see the tremendous actuation requirements, the angles and the load that we are applying. So here I would like to take the opportunity to thank publicly both ETA and LeArtiker in this particular case, because they really went the extra mile to get this to work. So in the end, we managed to reproduce the in-service failure mode, and we tested a redesign proposed by our supplier, by Metallo Caucho, and actually we observed that the fatigue life was extended by a factor of 40. So in the end, I mean, this was a very happy conclusion to a very painful project. So I'm running over time already, so I conclude the presentation. Rubber is a crucial element in rolling stock, and we've learned it the hard way. From being non-experts or knowing basically nothing about rubbers, we've had a very steep learning curve because of problems we've experienced in service. Obviously, it is known that rubber is a live material, you all know that, and you have to deal with it. In our particular case, it affects critically safety, comfort, and life cycle costs. This uncertainty makes our life a bit difficult because it requires very high safety margins. Sometimes it leads to unrealistic design specifications, and we make the life of our suppliers miserable by requesting something that cannot be done in practice. And on top of that, we also penalize performance and nominal conditions, because we've experienced projects in which the stiffening on the primary was above 30%, but we also have projects where we've observed a stiffening of the order of 10%. So considering a 30% really is penalizing a lot the nominal condition in cases when you don't really have this stiffening. Just a couple of areas of further work. We carry on working with the primary metacon stiffening, like I said, but another big area of interest for us is the condition-based maintenance. Direct monitoring would provide a lot of very useful information if we were able to know the loads that our primary suspension are subjected to, or the stiffness at a given time. At the moment, we only know it every 4 years or so, sometimes every 8 years. It's not enough. We don't know at which conditions they are operating. So being able to know this would be very helpful. An alternative to direct monitoring, intrusive monitoring, would be to actually do the monitoring on the track side. So this might lead to issues with the track manager, but in cases where we can actually do that through accelerometers and strain gauges, we are able to provide a guesstimate of the stiffening of our primary suspension. So this is not extremely accurate method, but what we've found is that for a safety perspective, it is enough. So this is an area of work that we are trying to explore further. And finally, I guess like everyone else, we are of course very interested in increasing the longevity of our materials, because if we can make them last for 30 years, like the rest of the train, that would make our life a lot better. So that was it. Thank you very much for listening, and well, I guess I'll take questions if there are any.
Thank you, Joseba. I think it was a very, very complete presentation covering a lot of topics related with elastomeric materials, modeling, characterization issues, topics that we have been also covering in the course related with DMA, all the modeling strategies. You have been also talking about the balance between the complexity of the models and the accuracy. You have covered all the different modeling hyperelasticity up to viscoplasticity models that we would say that they are the most advanced material modeling to predict all the nonlinear behaviors that we can have in the products. But at the end, I think that you have given you a picture of how these material models can be also applied in a product level. So very, very interesting presentation. I don't know if anyone has any particular questions.
Maybe Will, do you have any question about the presentation?
Yeah, hey, I was typing it, but maybe I'll just ask it. Can you talk a little bit about how many degrees of freedom it took to replicate the, you mentioned this experience with trying to replicate in-service failures. Were you able to do, how many degrees of freedom did you have to incorporate into your test bench to make that work?
It has, I mean, I guess you are asking, Will, about the test we did on the anti-roll system articulation. That has 3 degrees of freedom. Okay. So it is only 3 degrees of freedom. They are independent. There is the radial load, and then you have the angles. One is torsional, and the other one is conic or cardanic. It is 3 degrees of freedom. What we found is that 3 degrees of freedom doesn't seem so difficult. Well, perhaps some manufacturers have the capability of doing 2 degrees of freedom and fixing a third one, not being able to do the 3 of them independently. But there were more, I mean, we could find places where we were able to do the test with 3 degrees of freedom independently controlled. The problem were the loads. Usually these are mostly focused on automotive industry, where the loads are smaller than the ones in the train. So here we are talking the radial load in one of the projects is of the order of 90 kilonewtons. So it was, we didn't find any facility that had the capability of actually undertaking the tests without designing the whole test setup to be able to do it.
Thank you.
Yeah, we think we have some questions also in the chat from people.
A couple of questions. So Unai is saying, hello, Joseba. I would like to know, how do you determine the in-service load conditions? Thank you.
That's a tricky question. To be honest, we don't know. Like I said, until a few years ago, the design was mostly based on previous designs, and we didn't really know the real conditions. As we started seeing problems in practice, then we had to dig in and try to obtain more information about how our trains behave. I must confess that sometimes I found it very humbling to realize how little we know about the operating conditions of our trains. Particularly track irregularities, over which we don't have control, play a major role on the loads that the suspension experiences, and very often we don't know about that. And often the infrastructure manager won't provide that information either, because it might compromise their maintenance as well. From the 2 examples that I've shown for the anti-roll system articulation, we were able to theoretically determine what loads the bushing would experience. And then we actually went to the track and tested, took measurements, and in that case we were able to confirm that the scenario we were contemplating of like the 3 loads reaching peak value, maximum value simultaneously was correct, and also we got the value within a reasonable accuracy. So that was one. When it comes to the primary suspension loads, actually, we don't know. When we have to consider some loading scenario, usually we do it from simulations, from multi-body simulations. So we have the model of our train, we have a model of our track, we simulate it, and then we get the loading from that simulation. It would be very, very expensive to actually have measurements, real-life measurements of the loads in the primary suspension. So, like I said, we hope we will get to a point where we can have live monitoring of the loads and of the stiffness of our element. At the moment, we don't have that, and we need to rely on predictions, multi-body dynamic simulations predictions.
Perfect. Thank you, Joseba. And I think that we have a second question in the chat. So, hi, Joseba. Thanks for your great talk. I was wondering how you set up or which rubber model you use for the multi-body dynamics. And I think they are also asking about the level of the accuracy of this model.
All right. So essentially, until not very long ago, we actually had a linear stiffness, just a K for our simulations. So that was it. At the moment, we have some more sophisticated things. We do take into account the nonlinear curve. Okay, so the hyperelastic curve, we do take that into account. We model the force deformation curve. No hysteresis. So we usually take the average between upwards and downwards curves after a few cycles. We do a lot more testing right now, and I'm sure our suppliers can attest to that and can complain about this, because we've started requesting a lot more tests to be able to characterize our suspension better. So we know a lot more about the behavior. Even the hysteresis, we do it at different, we do static, quasi-static and dynamic tests. We do different frequencies, we do different preloads, which are the passenger conditions, let's say. We do different amplitudes of the cycles. But then when it comes to practice for the multi-body simulation, we just introduce the force deformation curve for the nominal case. And what we do is we introduce a stiffening factor. So we usually do the nominal conditions, and then we do the safety conditions in the worst case scenario. So we can have a 30% stiffening, for example, but we apply that factor directly to the nonlinear elastic curve. When it comes to accuracy, what we've found is that this is enough to guarantee safety and to comply with the standards. And when you have to certify a train, you need to do a test campaign of the final train. You have to do quite a few tests, and we have validated the models against those tests. So, and we've seen that they are good enough to be able to do that. So the EN 14363 is the running dynamics standard that defines what accuracy you need to have in your model. And actually we have our software certified by an external independent entity to perform virtual certification. So if you validate your models in some particular scenarios, you are allowed to actually do the homologation of your train virtually through simulations, and we are certified to do that. So the accuracy it's acceptable. So I know this is not a 1% accuracy type of answer, but I hope it is good enough.
Sure. That's clear, I think. Yeah. Mm-hmm. Thank you, Joseba. Thank you.
Thanks a lot, Joseba. So there is no any further questions. We will go with the next talk. Okay, so the next talk is coming from Avient company. So we have with us Elias Ariño. Elias belongs to the technical department of Avient since September 2017, based in Barbastro plant. Elias has a previous experience in the automotive industry for 15 years in mold design, part design, dimension analysis, and simulation. And he holds a European Master of Polymers and Transformation Processes, and he is also postgraduated in Engineering of Plastic Transformation. So, Elias, it's your turn.
Okay, good morning all. Do you hear me well?
Yeah.
Can you hear me?
Yes.
Yes, we can hear you perfectly.
Perfectly.
We can hear you.
Okay, thank you. So, good morning all. I'm Elias Agnew. Today we're going to present you our solutions related to sustainability within our TPE's elastomer portfolio. And initially we will give you some ideas of the reason of what is pulling us to develop and deliver more and more sustainable solutions within the TPE portfolio. We'll show you some solutions that are based in biosourced materials, both for PP overmolding and ABS overmolding. Also, the latest solutions available that are compatible for some food contact applications, and also in a second place, the TPEs with recycled content, which kind of recycled content we use, how far can we go with the recycle percentage within the solutions, the formulations. Also, recycled content coming from the ocean plastics. Some examples of TPEs with flame retardancy inside, also with recycled content. And last but not least, the near resound art with recycled content, PCR post-consumer, coming from the PVB from the automotive windshields that until now are wasted. Through the 8 ways that IBM is making to help customers to be more sustainable. Today we will see solutions based on bio content and also solutions related to recycling. We have solutions with recycled content, and we even have some solutions that allows the customers to make more recyclable the final parts. Why we have more and more available solutions and more developments ongoing? These are the main reasons. The first one is the side of the end customers. The customers are more and more conscious of the CO2 footprint of their consumption of parts and materials. They are more focused on green solutions, and they are more open, and they prefer more and more these kind of solutions. This makes that related to the buyer, when they are thinking of buying a new product, they prefer more and more these kind of sustainable solutions that can play a key role in the marketing differentiation. The second one is the government and regulation pressure. We have more and more norms, standards, and regulations, including tax increases related to prime solutions. So recycled content is a way of ensuring that we are online with this pressure and these regulations. And also we have the brand owner commitment for the running products through all the applications. We have for the packaging industry, both for cosmetics and spirit caps, they are using and increasing the volumes of use of solutions and materials that contain recycled materials inside, biosourced materials in it, and this helps to the packaging industry also to a better image and branding name for the end customer of their solutions. And at the end, this branding is more appreciated by the end customers at the end. Also from the electrical and electronics industry, they are maximizing the recycled content with a minimum of 20% of recycled content always been allergen-free to accomplish their standards. Also, the automotive industry is asking for solutions with a minimum of 20-30% of recycled content, achieving the same performance as for the prime grades, also related to sustainable politics within their companies, and also to have a more sustainable product at the end. And also for consumer applications like big, that it's a key customer for Avient, where we have even achieved to develop and deliver a TP material that is transparent, colorable, and with recycled content. You can see one example of this application for this women's razor on the screen, where you see the nice aspect of the end product, thanks to the key properties of the recycled content solution. We have more solutions related to sustainability in Avient. You can see we reduce CO2 footprint in the material production and also during the material transformation due to the lower temperatures of transformation compared to polyamide solutions. We have the new TPs with PVB, polyvinyl butyral content, coming from the auto windscreens. We'll see at the end. We also have biofol polymers, both in the resin base and in the fillers. The new NYMAX grades that are polyamides based on biosourced materials, and also resin grades with bio-based renewable content. You see below the links, you can dig deeper in the further details. The TPs that are bio-based, we have, as mentioned, both solutions suitable for overmolding on PP and ABS. And we see that within these solutions, we achieve a high content of biosourced raw materials for the production of these solutions. The application can be widely used for personal care, household appliances, consumer electronics, and packaging. And they deliver a performance at the same level as the prime solutions. That's a key question, but because at the end we search for the sustainability, but achieving also the right level of performance that allows to deliver the right engineering solutions to our customers. Within this portfolio of bio-based TPEs, we achieve a high percentage of bio content within, from 30 to 60% of bio-renewable content. Also a wide range of harness, from 30 to 70, with a good UV resistance and a good addition to the TPB base in case these products are overmolded. You see here the wide range of harness and the basic parameters we can measure on these solutions. The harness from 25 to 70, more or less, with quite good properties and with a low density in the materials. You see that after the UV test, here you can see two examples of the behavior and the performance of these materials against the UV. And after 3 hours, the change is color is good, it's acceptable. So they have a good behavior in terms of aging against the UV. We also made some tests at room temperature and also at 70 degrees Celsius related to aging of the materials. And after seeing the results, if you look into the values of the shear rate and the specific gravity, the modulus, the tensile strength, elongation, the TR strength, the values are online from the first day to after 6 months. That means that we achieve a high level, a great property retention after this aging test. That means that the performance you can achieve in the initial part will withstand the weeks and the aging with a proper aging and property retention. We also have bio-based TPEs that are suitable for molding with ABS and styrenic substrates. Also with a wide range of sort A from 40 to 70. Here again you see an example of one of our available grades in Europe with a 55 sort A solution in natural. Property retention after the aging of the materials. After 6 months, room temperature after 3 weeks at 70 degrees Celsius, we found a good level of properties after the aging test. We have also measured the bio content within our formulations in order to compare the theoretical bio content we establish in our production against the real value of bio content in our materials. For that, we have performed this SATM test in order to measure the carbon, the biocarbon inside the material. And as you can see, in all cases, we are slightly above the theoretical bio content. So it's more than a theoretical thing, more a declaration. It's a real value of bio content within the materials. And to end this part of the presentation, he uses two examples of TPEs biosourced that are suitable for certain food contact applications. The first one in the left is suitable for some yogurt applications, and the one on the right is suitable for cosmetic applications. For sure, if you have some project, it's up to us to check with our regulatory team if the solution proposed is suitable for your applications. The most frequently asked questions related to these materials, it's when we heard bio, somebody can think of biodegradable materials. That is not the case, as we have seen after the aging test of these solutions, we get a good property retention, so they are not biodegradable, they are biosourced. We use at the initial feedstock of our production of the compounding phase, we use biosource raw materials coming from renewable sources, from plants, and that way we get the right level of sustainability. Until this month, we had a biosource solution based on sugarcane, but from this month we'll get further solutions, further biosource raw materials sources available. And as you can see, we will expand our portfolio, including renewable sources oil coming from plants. We also have seen the determination of bio-based content using radiocarbon analysis. And up to now, we can offer you an estimation of the CO2 footprint for our materials in order to allow you to have some estimation of the CO2 footprint of the material and accordingly the final part. We switch now to the TPE solutions with recycled content that we call Resound RVX. For these solutions, we use recycled content in the initial raw materials we consider, and thanks to our R&D team, we have achieved solutions where we get up to 85% of recycled content. That is quite attractive for some customers that they search to maximize the recycled content and the sustainability on their products. Again, then they show a performance comparable to the traditional keys using a more sustainable solution that can be very attractive to all the applications where the marketing and the differentiation from one product to another makes at the end we get more success on the put in place in the market of the on end products. We will also see some solutions that they even use plastics recovered from the oceans, ocean plastics from ocean works, and these solutions are overmolded to PP. That it is a way to reduce the CO2 footprint, reduce waste, and also reduce the energy demand that we need to produce the raw materials and transform the raw materials. By definition, by this ISO norm, the 40021, reduce the reward with green and the scrap generated within the transformation engine. I mean, if one extruder or injector is recovering material and parts, they regreen it and they use it again in a certain percentage in order to continue producing parts, that it's out of the definition of recycled content. That is a common practice, sustainable practice in a traditional injector or extruder if the quality of the final part allows it. But we cannot consider this as recycled. We can only consider as recycled after this ISO norm the pre-consumer materials and the post-consumer materials. Here you see a flow chart of the origin of the recycled materials. The blue square at the left, you see that the material manufacturers delivers the prime material to the injection or extrusion agent, and within its facilities, it transfers the materials into parts. In this process, you see in the upper side the reworkable material that is coming from scrap parts and that can be reintroduced in the system, but this cannot be considered as recycled material. And we have two ways of recovering these materials. The materials, once transformed in parts, have a life of the product, and if everything goes well, at the end of the life cycle of the products, these materials are recovered, transported to the recycling agent. They have a selection, cleaning, and then a transformation into the form of suitable materials, and that way we can get post-consumer recycled materials that are materials coming from existing parts that are coming from parts that can have suffered all the agents along the life cycle of the product. The other way of getting recycled material is to recover scrap parts and material from the transformation process. These are materials that they don't have the right format in order to transform them. Maybe they are not in pellet forms. They have some parameter that is not suitable for the end application. And these materials that have always been in industrial ground, they have always been within industrial facilities, can be recovered, treated, and converted into post-industrial recycled grades. These are the two ways to get recycled grades. For the Rosan RVX, we get from 25 to 40% recycled content. And in order to maximize recycled content, in some cases we have a mix of post-industrial and post-consumer content. The post-consumer content we have in some solutions is ocean plastics. That's why you see a shark on the screen. We have an example with harness short A65, bondable to PP, suitable for injection. And the potential applications is, as you can see, all kind of applications: personal, consumer, footwear, houseware, durables, and so on. Here you can see a chart comparing the prime grades against grades with recycled content. And as you can see, in all these three examples, marked in light green, we get above 80% of recycled content within these solutions. And as you can easily see in the comparison of properties, we get the right performance on the materials that allow us to use it for this kind of applications. This is an example of this grade that contains post-consumer recycle coming from the oceans. That way, we have a double way of sustainability. We use the recycled content, and we allow the cleaning of the oceans. And in that case, we can get black compounds or dark green compounds. That it's due to the incoming color from the raw material source. And this is also an example of a TPE with recycled content where we achieve the frame rating of V0 at 1.6 with the use of recycled content. So that means we don't suffer any counter effect from using recycled plastics. And the last, but not least, I'd say, is our most recent family of products of TPEs with recycled content. And as you can see the source of the recycled content. In this family of Rosan R, we use PVB, that is reclaimed from broken automotive seals and laminated architectural glass. And the really good point here is that we can achieve the circularity for this product. That is the inner layer in the windshields that gives the right properties in order to avoid a break of glass parts within the vehicle. That could be a safety issue. And up to now, the only way of these windshields, and you have to bear in mind that each year around 75 million windshields are wasted. The only way was to scrap it on the scrap yard and to leave it there without any added value to this material. This mix of glass and PVB make it up to now not suitable to recycle it. But we have succeeded to get the right collaboration with a company that delivers us the PVB content from these windshields, and that way we give an added value to this waste, and we reduce this weight. And this is a much appreciated thing amongst the automotive industry that is willing to increase the recycled content, and also to increase the circularity of the products. You see, we have solutions from 55 to 55 short A, injection moldable, suitable for to be overmolded in polypropylene, and also these solutions can be delivered in natural form or glycerol form. Some of these solutions they don't have any foul smell, any lack of properties against the prime TPEs. So, as a summary of the TPEs with recycled content, it's good to know that they have a comparable performance to traditional TPEs with up to 85% of recycled content. As you see, We don't stop to develop new solutions related to this, as the PVB content, recycled TPEs, and the final goal is to reduce the carbon emissions, also reduce the gross energy needed to get the materials, transform the parts. As you know, the energy has an increasing cost, and it has a big impact on the price of the materials and so on the parts and the final product where they are assembled. And the customers, the companies, and the governments, they are willing to get more sustainable solutions with an improved life cycle analysis on this, and at the end to reduce waste and pollution thanks to our products. And some frequently asked questions. We can offer you most of our standard grades that are standard grades for the automotive industry, packaging industry, and so on. We can offer you these grades that are already on the market. They have already its place, but to offer them with recycled content. After all the knowledge we have developed in all these materials, we can gather the knowledge and experience we have with the existing TPEs and mix it with the knowledge on the sustainable raw material source, and give you a sustainable solution with the right performance for the end application. We have a high recycled content up to 85%, where we have a mix of post-industrial and post-consumer. In order to maximize this recycled content, we have a mix, and in some cases we have we can give you an estimation of the mix of the PIR and PCR, but it's a mix of both. They also we have grades also after the on-flex AF that are widely used in the automotive industry for automotive interior applications. We have solutions with recycled content that achieve the right performance for the odor, fogging, and automotive interior norms, including the VDA 2570, and with certain limitations in its application. We have also some grades suitable for food contact using recycled content. So here are our contacts, and thank you for your attention. You have any questions?
Thanks for giving us the point of view of sustainability of the elastomers. Because as you have explained, you have two different strategies. First one related with the bio content, and the second one more related with recycling content. So I'm sure that these developments that you have done for other sectors in the future can be used also in the transport industry. So, well, I don't know if the rest of the speakers, they have any question. Otherwise, we have in the YouTube channel, we have a question of Joaquin. He says, "Hi Elias, thank you for your presentation." And he's asking about the PVB product related with the automotive waste. And he's asking about which is the timeline for the product launch in Europe.
Well, for that case, we have take profit of the power of development of EV with multiple plants, and we have planned to launch these PVB solutions in Europe this month. So from this month, we will have these solutions available in Europe. They are already available in the US. They are already under production. We have already put in place the scale-up of the product. And from this month, we'll have these solutions available in Europe. So if you have some interest, we we are open to your request.
Okay, thanks. And also it's asking about waste content or recycled content of this kind of material.
For this kind of materials, we have start with the initial grades available. We'll have 25% of recycled content.
Yeah, 25. Great.
Okay, nice.
So I think this is interesting, these last developments you mentioned, because we see how Avient is using this way the scrap that nowadays is scrap for the transport industry, and how to use it to develop new TP materials. And as you have mentioned, I think that in terms of the harness, and as Joseba has also mentioned, in terms of comfort and all the new requirements that could be key and are going to be key in the new mobility, I think are interesting, because as Joseba has also explained, for comfort targets, usually we need low stiffness, and this short hardness that you have in this kind of materials could be interesting for this kind of application. So yeah, super interesting, these developments. Okay, so I think we do not have any other questions, so we can follow with the talks.
With the next one. Okay, so the next speaker is Wilmars. Well, what to say about Wilmars? He's one of our core partners, and also I'll consider also Will like a friend. Well, Wilmars is international leader in the failure mechanism of rubber and elastomers. Well, he's the founder and the president of the company Endurica, developers of world's first commercial durability simulation software for elastomers. And Will has received several awards for his scientific contribution, including the 2020 CIVETS Award from the United States Small Business Administration in recognition of the accomplishment in creating a cutting-edge technology. The 2017 Rubber Division, the ACC Arnold Smith Special Service Award. In 2007, Sparks Thomas Awards of the ATC Rubber Division, and the 1999 Henry Fox Award on the SAE Fatigue Design and Evaluation Committee. He served as editor of the Rubber Division American Chemical Society for Rubber Chemistry and Technology for 10 years, and he's also the past editor of the Tire Science and Technology. Will has authored or co-authored more than 50 peer-reviewed publications and holds 4 patents. He's a sought-after leader on what he calls the special effects of rubber and elastomers, including material characterization, product evaluation, quantitative models, crack nucleation, fracture mechanics, and fatigue life prediction methods. So Will, you're on.
Thank you for that kind introduction. It's really good to be here with you this morning. We've been working with Leartica for a number of years. You guys were one of our very first sort of partners, so it's really good to be here and engaging again. So the topic I've brought today, the title is Intrinsic Strength and Infinite Life Design for Elastomers. Let me get my pointer going here. And, if you, first of all, let me say durability is a huge topic space. And if you look at how people approach the characterization and the analysis of durability issues, there's a bunch of different approaches that people take. What I'm showing on this slide are, if you categorize those approaches, there's 4 big categories that we could talk about. So infinite, and I'll call them infinite life, safe life, damage tolerant, and fail safe. Now, in this talk, I'm going to spend most of my time just talking about the first one, but I think it's good to kind of put put that into context with you know with the rest of them. So what do we mean by these categories? Well, in the infinite life approach, what you're gonna you could say that the infinite life approach is maybe the very simplest approach to a fatigue analysis. And you know, a lot of materials, and this is true of rubber, a lot of materials, if you keep the loads below a certain limit, you can expect that cracks will not grow in a cyclic manner. So in a sense, setting aside the possibility of aging, you can you can talk about indefinite life or infinite life. So yeah, in the infinite life approach, we say, I'm going to design this thing. I'm not going to allow any damage to develop, and that's an approach. Now, it's the question you asked when you use that approach is, number one, what is that fatigue limit, and then of course you have to ask, am I above it or below it, and by what margin am I above or below that limit? Now, this approach really is, you can think of it as a go, no go type of approach. When you're using the infinite life approach, it does not tell you, if the life is finite, it does not tell you how long the part will live. If you want to know that, then you kind of have to move up to the next level of characterization and analysis, and that's what we would call the safe life approach, right? In the safe life approach, you come in and you say, like we saw with the talk on the train materials. I think that Joseba mentioned that there's a requirement of 8 years on some of the components for the train, rubber components, and so that's an example of a safe life criterion, right? You say there's a target life, there's a certain amount of time which corresponds to a certain number of cycles, and what we have to do when we characterize and analyze is we have to show that even though we don't have infinite life, the number of cycles that can be sustained is adequate relative to that design target. So that's safe life. Now, if you're going to use the safe life approach, not only do we need to know what the fatigue limit is, but then we also need to know other things about the material, right? We need to know the fatigue crack growth rate curve, and more details of the material behavior. So the safe life approach, requires more experiments. It requires a deeper level of analysis. Now, of course, if you say, give me a design, a target life, typically that means that we're repeating a load case, right? So, when I say 8 years with 1 million repeats of what? Well, in the safe life approach, we kind of assume that the load case is very well defined, and then it's the same for every repeat. But a lot of times in real life, the load case is not the same every day, right? The load on day 1 is different from the load on day 2, is different from the load on day 3. Every day has different loads. And in that case, we kind of have to acknowledge that, that the life of the part really depends on the actual use history. And so we can talk about, well, maybe we have to monitor the progress of damage in the part, either with sensors or with calculations. Maybe we have to do some inspection of the part periodically. Maybe we predict remaining life on a part. But this is what we call a damage tolerant approach, right? We're saying, yeah, I know that this part can develop damage. I'm going to keep track of that. So that's the damage tolerant approach. And then the final approach, and maybe the most sophisticated, maybe the best practice approach would be what we call fail-safe. And the idea in fail-safe is that you just, as an engineer, you say, okay, I know this thing is going to fail at some point. How do I design the situation so that when it does fail, it's not a disaster, right? It's there's a secondary load path. There's an assurance that a failure does not lead to to a disaster. This is and the fail-safe approach is where things like, if you follow the digital twin idea, that's an example of a fail-safe approach, because when the damage develops to a certain point, you can send somebody an email or light up a light on a dashboard that says, "Hey, please change the part out because you've used up its life," and so that's an example of fail-safe. So yeah, like I say, if you've been following Endurica, we've been talking about the safe life, the damage tolerant, the fail-safe. We've been talking about those for a long time. Recently we've started to we've realized that there was kind of a gap in the solutions that we offered, and so we've relatively recently, last couple years, have been working on developing an offering to fit into the infinite life approach, and that's really what I want to sort of talk more about today. So that's why what I'm showing here is kind of a mapping between these different categories of approaches and the different software tools that we develop, right? We have 3 software tools. One is CL, one is DT, one is EIE. Each of these fatigue solvers solves a different type of problem, but you can see here how they map onto these categories of problems, right? If you want to do infinite life, there's a new feature in CL that will calculate your safety factor, and that's what I'm going to talk about in this talk. For the safe life approach, you could either use CL or DT. DT is if you have a block cycle schedule, you could model that and then calculate repeats of the whole schedule, and so on. But yeah, like I said, today we're going to talk about infinite life analysis. So all of these approaches are all built around the idea that your material, even when it's brand new, is full of microscopic features of the material that under cyclic loads can grow and develop as cracks, and it's also that development is also manifest as changes to the stiffness of the material. But yeah, all of these approaches can involve basically it involves the necessity of measuring the crack behavior, right? So we have to know, with regards to crack precursors, we have to know how big are they at time 0. That's a very important characteristic. It's governed by things like the ingredients of the rubber, the type of the polymer, the manufacturing process. But bigger crack precursors lead to shorter life. Smaller crack precursors lead to longer life. Another thing that we have to think about is crack drivers. This, so if you've got a crack of some size and you apply some loads, those drivers represent the energy that's available to drive crack growth, right? It's what is the driving force? So the higher the loads, the higher the strains, the faster cracks will grow. In some ways, that's controlled by stress-strain behavior of the material. It's controlled by mode of control. So whether you're force control or displacement control, those are all factors that sort of come under the category of crack drivers. And then finally, the last thing that's really important to look at in this is to look at the behavior of individual cracks. In other words, if I'm feeding a crack energy at a certain rate, is that enough to start the crack growing? And if it is, how fast does it grow? So these are the big questions that all of these approaches are founded on. Now, if you look specifically at the crack growth rate curve for an elastomeric material, this chart here kind of shows the typical behavior that we observe over a very wide range of rates. A couple of important features on this curve. Let's see, the x-axis is what we call the tearing energy. Basically that's a measure of how hard you're pushing the crack, right? So higher loads, higher strains, that's higher tearing energy. Crack growth rate, that's how quickly the crack is developing. The upper limit is what some people call the tear strength or the rupture strength, TC, right? The critical tearing energy. If your tearing energy exceeds the value of TC, then what you have is a crack that grows very, very rapidly, so rapidly that it's not a fatigue problem anymore, right? It's a strength problem. Right, so rubber has a tear strength, and that's kind of the upper bound of the crack growth rate curve. Now there's also a lower bound, and this is what we would call the fatigue limit, right? T naught. That's a value of the tearing energy, and if you're below T naught, then at that point you're not supplying enough energy to the rubber or to the crack, that there's just not enough energy to break polymer chains that cross the plane of the crack, and so the crack can't grow. We also call this the intrinsic strength because really this fatigue limit represents the energy that it takes to break the covalent bonds of the polymer chains that are crossing the plane of the crack. Now, usually when you're driving a crack at some rate, you get a tearing energy. That tearing energy is the sum of T naught plus an additional component of energy that comes from energy that's consumed in the crack tip process zone. But if you get rid of the process zone, what's left is just the intrinsic strength of the material, and that's really the same as the fatigue limit. Now, between these limits, you end up with a sort of a characteristic slope. I've called that F here, and that just sort of tells you the sensitivity, let's say, of the crack growth rate to the tearing energy. So for natural rubber, it's very common to see numbers like F equals 2. For synthetics, like SBR, you might see values like F equals 4. So that's kind of the common behavior. Now, when we're talking about infinite life, we're really going to mostly be concerned with T naught and where am I with respect to T naught? Am I below? Am I above? Am I below? If I am below, what's the margin that I have? Like I said, the intrinsic strength represents the energy it takes to break polymer chain. So here's a picture of a crack growing through a bit of rubber here. And you can see sort of pictures of the polymer chain. On one crack face, the polymer chain is attached by a crosslink to the rest of the rubber network. And on the other crack face, it's basically crosslinks where the polymer chains are attached. And so the crack is always breaking the segments of the chains that come between crosslinks. And the intrinsic strength is just that minimum energy that it takes to grow a crack and to break all of the chains per unit area. There's a great paper on this, Lake and Thomas in 1967, where they basically propose the model that we've kind of been using ever since. It's basically built on the idea of breaking polymer chains. So the question then becomes, well, so we know rubber has a fatigue limit, and I know that if I stay below it, I've got infinite life. How do I measure that intrinsic strength? Now, I'll call it a naive approach. A naive approach might be to get a fatigue crack growth test system, right, servohydraulic, and run a fatigue test and basically sort of take this curve and go to lower and lower and lower crack growth rates until you approach this limit. And I call that naive because if you try and do that, what ends up happening is you end up running really, really, really long tests. And you end up burning huge amounts of time on expensive machines. And so there's advantages to sort of coming at this from a different angle. And that's what we're going to do in this approach. Now, in the work I'm going to show you here, we've partnered with a German company, Coesfeld. They've implemented the procedures that we're going to show you here on a piece of hardware that we call the intrinsic strength analyzer. The idea of this machine is that it directly measures T naught, And the beautiful thing is it does it in about an hour, which is really an impressive feat. Funny story here. We once had a client that wanted to measure. It was in the electronic space. They were working on an elastomeric speaker cone, so they were worried about fatigue at very high frequencies, like 10,000, 20,000 hertz. If you've ever tried fatigue measurements at those types of frequencies, you start to worry a lot about how much stroke you can get and how much power you have to feed into the machine. And what we ended up doing for that customer was using this intrinsic strength measurement. We just said, hey, look, it's really hard to measure at that high frequency. Maybe we could, just make sure that we're below the fatigue limit, and that way you've got infinite life, and you can stop worrying about frequency and temperature. So that was an approach that worked in that particular case. Now the procedure that this instrument uses was a procedure that was pioneered by Graham Lake and Eun-Hak Yeo. In fact, I believe this was Eun-Hak Yeo's PhD thesis. The method is based on cutting the rubber with a very sharp razor blade. It's when you look at the test, sometimes people scratch their head initially because they're like, "Wait a minute, this is not a fatigue test," and that's right. It's not a fatigue test. It's actually cutting the rubber with a very sharp razor blade. The blade is instrumented so that we can measure the forces that act on the blade. We use a blade that's as sharp as you can possibly get. It's a blade from a microtome, so it's nanoscopic sharpness. And the idea in the experiment is to drive the blade through the rubber at a series of different. There's a matrix of things that we do, but when we push the blade through the rubber, we do that with the rubber stretched and strained a little bit. And typically we'll do this under a series of strain levels, maybe 4 strain levels. At each strain level, we go through a schedule of different cutting rates. So you can see on the bottom plot, so that on the bottom here, I'm plotting the rate at which the blade is progressing as a function of time. So you can see for during the period of strain 1, first I go through an equilibration. So this pink region here, right? I stretch the specimen, I put it at strain 1, and then I hold there for 5 or 10 minutes, depending on how you set up your test. And the point of this is before you do the cutting motion, you want the rubber to be in equilibrium. We're trying to get rid of any dissipation, viscoelastic dissipation that could happen in the rubber. So you want to give it time to equilibrate. And then once it's equilibrated, then we begin pushing the blade into the rubber at a series of controlled rates. So we start at the highest rate, and then we reduce the rate by a factor of about 100. And then we reduce the rate again by about a factor of 10. The idea being that, as you're cutting, again, we want to eliminate any viscoelastic effects in the material. And so by cutting at slower and slower and slower rates, the viscoelastic effects get smaller and smaller. And so by measuring this over a few rates, we can observe that and just make a verification that we've succeeded in eliminating those dissipative effects. So this is the basic schedule of things that happen during the test. And that produces results that look like this. So this is a material. This is actually a grommet material. So here's a picture of the grommet. This was for an air compressor application. Again, this is another high frequency application. The grommet is a very inexpensive component. And so a lot of times the engineers working on these don't have the, let's say, scope in their projects to do a full characterization. But measuring the intrinsic strength is certainly doable. so that's what this material is. Now, when we run these measurements, typically what we'll do is we'll run two materials. We'll run the material being characterized. We will also measure the a control material, and I'll talk about why we do that here in a minute. But so these are results for the grommet material and for the control. Now, what you're looking at is a plot that has two axes. The x-axis is the tearing energy that acts on the crack that is due to straining of the material. So we're using a planar tension specimen. If you're familiar with crack growth measurements, same type of specimen. And the tearing energy is just the product of the strain energy density times the height of the specimen, just like it would be for a traditional crack growth test. So that's what you see on the x-axis. The y-axis is an additional contribution to the tearing energy that is coming from the blade, right? So I mentioned that we instrument the blade, so we're measuring the forces, and if we know the forces, we can calculate the tearing energy that's due only to the blade. And what we do is we construct this plot of cutting energy versus tearing energy, and you can see I've plotted these for the three different rates. And what you see is that at the high rate, you're measuring higher energies. As you slow the measurement down, the curve kind of converges. And really what you're trying to estimate is what would be that curve under conditions of zero, basically very slow crack growth. Now, what we're interested then is the total of the cutting plus the tearing. So I've plotted a red line here. That red line is basically the line along which the sum of the cutting plus the tearing energy is equal to the minimum observed total sum of energies, right? So we're trying to minimize that is really the thing, and that red line, that total energy is minimized basically at the point that the point on the lowest rate curve that just barely touches the red line. In this case, that works out to a cutting energy of about 1,000 joule per meter squared. If you extrapolate these to the axes, you could say, well, the cutting energy here is 1,000 joule per meter squared, and so now this is a smaller number than the tear strength of the rubber, right? And the difference between those represents the dissipative part of the strength of the material. Or if you extrapolate this back to the y-axis, this would represent, if you could somehow eliminate friction and eliminate any contribution of opening the crack, this is the energy that it takes to push the blade through the rubber in a frictionless manner. So that's kind of what this curve represents. Now, what Lake and Yo showed in their original paper was this cutting measurement is an indicator of the fatigue threshold. It's not the fatigue threshold itself, but it is proportional. They measured a series of different polymer systems and showed that these things are correlated. And that's why we need the control materials, because for the control material, we know the absolute value of the threshold. And so if I measure the cutting energy for both of these, that means I know the relative cutting energy. I take that ratio. And if I know that the control material has an absolute threshold of 47, then I can calculate the threshold for the material being characterized by taking a ratio, right? So here, 1100 is slightly bigger than 10, than 1000. So the threshold of the grommet would be slightly bigger than 47 joule per meter squared. These are the results from Lake and Yo, showing the correlation between the cutting method, right, the ISA test, versus running a very, very long crack growth test. Very strong correlation, goes right through 0, 0. This plot over here is for the grommet material, right? So you can see the grommet. The grommet ended, in this case, the grommet ends up with a threshold of 42 joule per meter squared. Now you could say, well, okay, it's fine to read Lake and Yo's old paper. Has anybody ever repeated that work? For the first few years of this, we got that question a lot, and so we finally did go and repeat this work, and we actually ran a very long crack growth test. So there's two sets of results here. On the left, you're looking at results that were measured on the Coesfeld-Terran fatigue analyzer. That's a dynamic system that can measure the fatigue crack growth rate curve. And in 5 days, you can reach down to a crack growth rate of about 10 to the minus 7. But in order to observe the fatigue limit, you have to keep going. And so we actually did run a test for about 8 months to get us down to a rate of about 10 to the minus 9. So these are the raw results doing the fatigue crack growth. We don't do this obviously very often or very much because it's just insanely expensive. And you can read about this here. There's a paper that we co-authored with Radek Stocek that you can read about. But so we basically compared the threshold that we estimate with this method with the threshold that we measure with the ISA. And in fact, the comparison is very, very good. Different by, in this case, happened to be less than 5%. So, very, very strong correlation. So anyhow, so that's the ISA method. Now I want to let's take and apply the method to two materials that we know a lot about. So natural rubber and butadiene. So what you're looking at here, these are fatigue crack growth rate curves for these two materials. And what's interesting to compare about these materials is they have a different power law slope F, right? I've characterized that here. I've got a table that shows the tear strength values TC. Natural rubber is much stronger than butadiene by about a factor of 6. But butadiene, it has a much steeper slope for the for the fatigue slope. So for natural rubber, we have about a value of 2 on F. For butadiene, we have a value of 5. And so here's what you get for the crack growth if you're running a traditional fatigue crack growth test. And what I want to say is using the intrinsic strength measurement, you can get a very approximate estimation of the fatigue crack growth rate curve. I like to call this Robertson's rule. Anybody who knew Chris Robertson while he was working with us, this is a correlation that he kind of came up with. But what he noticed was that if you sort of draw a line at a rate of 10 to the minus 2 millimeter per cycle and 10 to the minus 8 millimeter per cycle, if you just draw a line and intersect that with the crack growth rate curve, then if you take the tear strength and if you take the intrinsic strength and just connect those dots with an assumed crack growth rate of 10 to the minus 2 and 10 to the minus 8, that the curve that you get actually looks a lot like the slope that you measure with a full crack growth rate test. Now you have to be careful because I don't want to represent that this is a highly accurate way to characterize the whole crack growth rate curve, but it is a way to very rapidly estimate. So in this case, for the natural and the butadiene, we have these values for the threshold and these values for the tear strength. Skip ahead here. And so if you take this, I call it, like I say, Robertson's rule. If you take Robertson's rule and calculate the slopes just based on these assumptions, then these are the calculated slopes that we estimate, right? For the natural rubber, which had an actual slope of about 1.9, we end up with an estimate of 2.3. For the butadiene that had an actual slope of 5, we predicted a slope of 4. So like I say, not perfect, but if you want to measure these things in an hour, let's say you're comparing compounds, you want to measure 10 compounds, this is a very rapid way to make quick estimates and sort of down select on which materials you're going to work with in the long run. Here's kind of the Chris took this data set. We actually had data across maybe 20 or 30 compounds where we had both the intrinsic strength and the crack growth measurement slope F. And so he basically made a plot showing the result of his quick estimate versus the F that we measure in in crack growth experiments, and that's what you're looking at here. So again, you can see that the correlation is not perfect. It seems like when you get to higher values of F, maybe we are predicting values of, or our predicted values are maybe a bit too high. But they are strongly correlated, right? I guess that's the main point. So the practice that we recommend to people is you should think of this intrinsic strength really as a sort of a low resolution, it's a low resolution version of the crack growth rate curve. If you measure T0 and TC, that puts you in a position to get a rough picture of things. Now, if you want to get the detailed picture that you would maybe use in a full, deep, safe life approach analysis, then you're going to use a fatigue crack growth test system. But if you just want to do compounding type studies, low resolution sometimes is enough. Okay, so that's Robertson's rule. And so that's basically what I wanted to say about materials characterization. Now I want to sort of switch topics a little bit and talk about, okay, so you've measured your intrinsic strength. How do you use that in analysis? And the analysis is actually very simple. We're just going to compute the ratio of the threshold to the energy release rate that occurs for a crack in your material, in your application. Now, of course, the question then becomes, well, which crack? So what we do in analysis here is we look at if you build a fine element model of your part, you can look in the results for each element of your model. And in each element, you could say that the crack might take any of a number of possible orientations. This red disc here is a representation of a penny-shaped crack. And what we do is we repeat this calculation for all possible orientations of a crack in every element. And for each of these orientations, we say, what's the ratio of that? If I calculate the energy release rate for that crack and I compare it to the intrinsic strength, what's that ratio? And what we do is we make a search to find the orientation of crack that minimizes that safety factor, right? Because that's the orientation that minimizes the safety factor is let's say the most critical, right? And so in fact, this is what we call critical plane analysis, because we're searching for the particular crack that experiences the worst load case, and that's going to be the one that minimizes this safety factor. So this is a feature in Endurica. If you know your threshold T0, you feed that into Endurica, you give it your fine element model, it does the critical plane search, and it gives you a contour plot where you can look at the distribution of safety factor on your part. Like I say, the safe life analysis is one that you might use on very inexpensive parts like this grommet. So if we had measured the threshold at 800 joule per meter squared, if we knew the crack precursor size was 100 microns, if we knew the shear stress was 3 megapascals, then just with that small amount, the other beautiful thing about this safe life approach is it doesn't require a lot of materials characterization, right? We don't have to understand temperature or frequency effects. We just need to know this limit. We need to know the precursor size. We need to know the stiffness of the part. And at that point, we're in a position to calculate safety factor. So here I'm going to do this for the grommet at 3 different load cases. I've got 3 degrees of freedom here. an X and a Y and a rotation. So these are load cases from the what do you call it? The air conditioning application. And what you're looking at here are animations of the finite element model running through that particular load case. So this is the small load case, and what you're looking at here, the colors are showing the computed safety factor. So it's just the ratio of threshold to actual load of the worst possible crack at each spot. Red, so the value red is a safety factor of 1. So if you see a value red, that means that basically you're right on the line. Anything colder than red is a safety factor that's bigger than 1. And in this case, the worst safety factor is in this corner. You can see it's just a little bit orange, maybe. And if you click on that and sort of open it up, you can find out the safety factor in that worst case is about 2.6. So this tells us that we have a margin of about 2.6 on the crack driving force. So yeah, this we would say this is safe, right? It's we could expect infinite life. Like I say, for the moment, ignoring aging. You might want to. Aging can change the threshold, so you do have to think about that. But anyhow, so that's the small load case. Here's the medium load case. Now, in this case, we actually you see this element that's colored black. Where you see black, that those are locations where the safety factor has become less than 1. And so that's a case where you would look at this and then you would immediately say, oh, this part will not last forever. How long will it last? I don't know. I need to, now I need to go to my safe life approach instead of my infinite life approach. But yeah, so that's an example of the medium load case. Here's the high load case. Again, this one's not going to be infinite life. We're exceeding we're going below the fatigue threshold. The safety factor is 0.43. So basically you're not getting infinite life out of this. So we would have to go to a safe life approach. So that's an example for the grommet. You can do this with almost all sorts of things. Tires have very long fatigue lives, especially the carcass of the tire. So these are calculations of the safety factor for a tire. And this is under just nominal conditions, 100% load, straight ahead rolling, full inflation. And in this case, we calculate a safety factor of about 4. And the place where the safety factor is lowest is right at the belt edge of the tire. So here we've measured fatigue threshold for all the different components in the tire. So that's an example from a tire. Another example would be a fertilizer squeeze pump. This is an ag application, right? So basically, you've got fertilizer in these tanks, and you need to pump it out onto the field. The way the pump works is these tires drive a roller. The roller rolls over these hoses, and when the roller rolls over the hose, it basically pulls fluid along, right? So here's kind of an animation of the rollers rolling over those 6 hoses, and you can see it pinches off the cross section and pushes fluid through the hose. And so we've made a model of the hose here. You can see this is a zoom up of just the section of the hose that's getting crushed. And you can see there's a stress concentration on the inside diameter of the hose. We've done the safety factor analysis here and learned that we have a margin of about a factor of 6 in this case for this hose. So again, very simple analysis. As soon as somebody raises their hand and says, well, how long does it last? Then you've got to go actually, do a deeper level of characterization and analysis. But yeah, very simple thing. So so that's kind of an introduction to the idea of intrinsic strength and its utility. I guess I'll stop here and just say that the intrinsic strength analyzer is great it's great as a screening test. It's great for getting this T-naught that you can use for doing the infinite life analysis. You can use it with Robertson's rule. So I'll stop here and take questions.
Thank you, Will, for your kind presentation where, well, you have covered a lot of aspects related with the phenomenology and mechanisms that govern the fatigue of elastomeric materials and how to apply all these modeling approaches to be able to predict the fatigue behavior of elastomeric components. And I think that it has been a good fatigue introductory presentation also for the next presentation that we will have at 11:30 after the coffee break, because in this presentation also Metravip is going to introduce the new innovations and developments they have in terms of how to capture, characterize crack growth and perform crack growth testing by means of DMA.
Okay,
Wonderful.
so well, maybe before the break, we have just the option to make a short questions. We have here, for example, there are two questions, but we can select one. Aitor Arriaga, it's asking concerning on the growment component, very high frequency application, so it's 10,000 Hz. I wonder how could we capture the material properties at such frequencies in order to perform realistic simulations.
Yeah, so I guess the question there. So in the simulations we've done here, I think when you're using the safe life or when you're using infinite life approach, you're probably going to do that within the context of for purpose of fatigue work, you're going to use hyperelasticity. Now, I guess what we haven't talked about is at those kinds of frequencies, you also have to think very carefully about self-heating. That's probably the bigger issue at those high frequencies. If you're operating below threshold, you can do that indefinitely. You can estimate a stiffness just using a dynamic a dynamic test. But even if cracks don't grow, if you're at 10,000 hertz, it's very easy to sort of overheat the component, and there are failure modes that you have to think about from overheating. So at that point, you would want to characterize scholastic behavior. You'd want to understand loss modulus, and that gets into a whole new topic of modeling temperature distribution in the part. Mm-hmm. Yeah, good question.
Okay, thanks. So, well, we have reached to the break. So we have now 15 minutes for just drinking a coffee or whatever you want. Okay, so we'll be back in 15 minutes. Thanks.
See you soon.
All right. Thank you.
So, hello everybody. We are here. So after the coffee break, and as you see, now with me we have Brice.
Hello.
So first of all, before the talk of Brice, I would really like to thank a lot Brice and also Matthew, which are the two colleagues from Metravip that have been involved in all the preparation of this DYNAeLAST event before and also during the course. It was a pleasure to have you here, to have time to know each other, and of course to share all the knowledge we have and all the scientific issues in order to help each other in the new developments and innovations in terms of dynamic mechanical analysis and testing. So, very briefly, I will introduce Brice. So Brice did a PhD in material science in partnership with a major French industrial group. And then in 2016, he made a professional transition by taking responsibility for the sales of characterization instruments. And nowadays, he's currently in charge of the European market for the material testing part of ACOM. And he's focused on dynamic mechanical analysis. So, Brice, I don't know if you would like to add something else about you,
perfect.
or we will go.
Kind introduction.
We will
really
go
perfect.
through the presentation. So
Okay.
we will share our screen. Here is it, and view full screen. So, Brice, you have the power now.
Okay, that's my turn. So thank you, Rossetti, for this kind introduction. I would like to discuss with you about innovation in rubber compound Crack-Growth testing with DMA. I'm actually the European sales manager, and I share the results and the presentation with my dear colleague, DMA expert Mathieu Badard. So just a brief summary, I would like to introduce Metravib and Aquem Group. I would like to share with you some DMA backgrounds, the introduction of the new Crack-Growth system we produce now, and some experimental results to finish by a classical conclusion. Just first of all, who are we? Who are exactly Aquem? Aquem is an international French company with a turnover of 130 million euros. We are almost 800 employees all around the world. We are working with more than 200 partners, and we have subsidiaries all around the world, mainly based in US, in Asia, in Australia, and of course our headquarters are in Lyon, at the center of France. So our mission is to provide organization with better opportunities through focused data and technology. We have several business units in Aquem. First one focus on industrial reliability, another one on emission and process, ambient monitoring, protection, that is a defense activity. We are working with Army all around the world. And the last one, but not the least, a design business unit, Metravib, contributing to effective, robust, and noiseless produce. And just to focus on this activity, two branches. First is an engineering group, the expertise in the field of noise and vibration engineering and material testing. Our goal and my goal is to provide industry and research laboratories DMA instruments for all characterization of thermomechanical properties of materials. Our customers are focused on transport industry, aerospace, oil and gas, engineering, energy, etc., etc. Okay. Just a brief focus on our DMA instrument range and application in order to give you some idea. We propose three kinds of family of DMA. First one, low force DMA with DMA 25 and DMA 50. A very cost-effective instrument, easy to use. Just a simple electric outlet, and you can perform all classical DMA tests you want. Another family, DMA Plus series, three different instruments with DMA Plus 300, DMA Plus 1000 and 2000. 300 is maybe the more polyvalent machine we can propose. DMA Plus 1000 is focused on polymer, composite, and elastomers field, and DMA Plus 2000 is mainly dedicated for tire industry. With this DMA Plus series, you can add an automated system, an automated DMA with expander, and we can propose more than simply DMA characterization as fatigue capability, fatigue testing with yield buildup, and of course, Crack-Growth testing. Finally, we can propose another kind of DMA named DHF104 for very high frequency 10 kHz. Actually, this is a DMA, a specific instrument in order to have direct characterization up to 10 kHz. This is a small map about our customers. So as explained, mainly focus on tire industry, but more and more in composite and polymer field. We have an international market. 80% of our customers are in the international market, mainly in US, China, Japan, and India, of course, and Europe. So, DMA background and DMA principle. DMA, it's just simple, consisting in applying a dynamic excitation to a materials, and we measure displacement and force, dynamic displacement and dynamic force through an electrodynamic checker. So, force divided by the displacement, we can compute and you can measure the stiffness, the complex stiffness, of course, and from the specimen shape and dimension of the specimen, We can compute the modulus, Young modulus if you work in tension compression, or shear modulus if you work in shear excitation. Tangent delta, representing the damping properties of your materials, is just K second or divided by K prime, or a second divided by a prime, just to give you the example. We propose several various excitation modes depending on the nature of the material you want to characterize. For instance, for rubber, mainly we use compression, tension, but also a shear mode, double shear mode or shear for film. For polymer industry, we can use the tension mode and the bending mode, 3 points bending, double cantilever, or 4 points bending if you want to have some fatigue capability, etc., etc. We can measure also bituminum, some paste materials, metals, alloys, glass, ceramics. We can propose a lot of different materials according to this various excitation mode. Typical DMA data, classical DMA test. First at all, maybe temperature sweep in order to characterize some transition, alpha transition or beta transition. As you can see just on the picture, the evolution of E prime as a function of the temperature, the tangent delta, and the evolution of E double prime on the same characterization. Another one more important measure is the strain sweep. You have an example on a rubber material in order to characterize pain effect, that is to say the linear behavior and the non-linear behavior of your materials. And if you want to go back, you can characterize the Mullin's effect and a strong effect on the viscoelastic properties, especially on the damping properties. And the last one, frequency sweep, just the behavior of your materials as a function of the frequency. Very low frequency, up to 1000 Hz in option on the DMA Plus series instruments. So here we are talking about crack growth testing. Actually, we propose a new product for 1 year now, an automated system in order to characterize crack growth rates. This system is available only on the DMA Plus series, that is to say DMA Plus 300, 1000 and 2000, because we use a specific software for that named Multitest instead of DYNAeLAST, who's in charge of simply DMA characterization. So Multitest, we can have a perfect control on the waveform of the signal, sinus, Eversine. Eversine is a type of signal we can use in tire industry. Triangle, square, etc., etc. We can control strain, displacement, stress, and force. And just to give you some technical specification about DMA Plus series, we can apply a maximum displacement range plus or minus 6 millimeters from a frequency range of a very low frequency up to 200 Hz and 1000 Hz in option. For this system, mainly focus on crack growth, the maximum temperature we can reach into the thermal chamber is 300 degrees. And of course, we can decrease the temperature with liquid nitrogen up to minus 150 degrees. So what is a crack growth system? This is a picture from a DMA, including a dedicated optical system. Just here you have the specimen. We have different size of specimen, pure shear specimen with a width of 40 millimeters up to 80 millimeters. The thickness is at maximum 2 millimeters and the height between grips is 6 millimeters. In this picture, the DMA used is the Metravib DMA Plus 2000. That is to say plus or minus 1000 Newton, plus or minus 6 millimeters up to 1 kilohertz, waveform control, etc. And we use a dedicated optical system which composed with a micrometric motorized table, a high resolution camera, and a lens magnification, allowing us to have a follow on the crack tip precision up to 5 microns. So how it works? First, the camera can focus automatically on the crack tips. You have an example just here. Once, just after, the DMA can apply a deformation to the specimen, for instance, a sinus signal, sorry. 3, the camera can focus automatically on the new crack, and once again, the DMA apply a deformation and record the crack growth. So, system is quite simple. Just to summarize, crack growth test, we need 3 different steps process. The first step is stabilization test in order to apply a certain number of cycles at one frequency at one strain amplitude in order to avoid any pain and Mullin's effect, essential to take into account the pronounced hysteretic behavior of field rubber compounds. The second step is characterization step. The aim of this step is to get the relationship between the tear energy, the tear energy as a function of the strain. G actually is totally fully independent on the crack growth length, and they can be characterized before cutting specimen. And the characterization test consists in applying a strain sweep from low strain up to the highest strain amplitude to be applied in a crack growth test. Mm-hmm. Okay, and G-curve, the G-curve obtained can allow to have a smart comparison between various rubber and various elastomers in similar testing conditions. Sorry, don't move. Okay, and finally, the last. Okay, this one and this one.
Yeah.
Okay, sorry. And finally, the last step is to generate the crack. First of all, the specimen is pre-deformed, and you can make initial crack with a scalpel, generally with a length of 5 or 10 millimeters. And depending on the width of your specimen, you can cut 2 cracks or 4 cracks with 80 millimeters. So you can follow with this kind of specimen 4 cracks at the same time with the system. So the camera localized all cracks. We apply a static force or strain to open the cracks. We select a characteristic point, which will be used as a reference point. And as each crack tips is located by the camera. You have an example just on the picture below the slide. We apply strain with DMA. That is to say, we can have a control on the frequency, on the waveform, on the amplitude of the number of cycles, and of course, as a function of the temperature. So how those parameters can impact the crack growth? So we're applying a strain with the DMA. The DMA finds and records the growth of the crack tips. And just to give you an example, the operators define arbitrary periodic measurement of crack growth tip, for instance, every 10,000 or every 50,000 cycles, depending on the tearing energy they want. For instance, 50,000 cycles for a low energy, G300, and 2,000 cycles if the tearing energy is much more higher, for instance, 2,000. And after that, we will go back to the step C, that is to say, applying another strain, and etc., until the end conditions are fully fulfilled. Okay, these successive steps are fully automated. Just to sum up, crack growth measurement is performed as follows. Apply a short preliminary cyclic test to blunt the crack tips. Stop of the excitation after a programmed number of cycles. Apply a programmed static force strain to open the crack. Target each crack tips and take a picture. Process the image in real time to obtain the crack tip position or coordinates. store each crack picture systematically, and restart the excitation. And we can restart the excitation with an amplitude of 80% from memorized waveform before previous stop. So the whole process is fully automated. And just to give you an example, in order to follow 4 cracks at the same time, the duration of the crack growth measurement sequence is about 50 seconds. So what about the monitoring parameters? That is to say, first of all, the stability of specimen position. In order to ensure the absence of specimen slippage inside the grips, could be happen, a reference point is systematically selected at the beginning of the test. You have an example on this picture, for instance, and the coordinates of this point are systematically checked before each crack tip position measurement. This is an easy detection of potential wrong test condition, and this is especially relevant when using not mold specimen intensive grips, where the risk of specimen slippage is much higher. What about crack follow-up criterions? All criterions are, of course, adjustable. The distance between each cracks have to be up to 15 millimeters. The crack deviation angle is up to 45 degrees. And the crack growth rate dispersion between all the cracks on the same specimen have to be about 200 nanometers per cycle. This is just a recommendation. And the automatic test stopped by crack growth rate stability monitoring, we can have a programmable tolerance for a programmable number of consecutive data points. So this was just the introduction. I would like to see some experimental results. What kind of curve we can obtain with this system? The curve I will introduce was shared by ELASTCP, a French group, and with Nathan Céleste, with the engineer in charge. First, typical experimental results: the crack tips position and the crack growth rate versus the number of cycles. For one and just one tier energy, 3000. The evolution of the blue curve is the crack growth rate, nanometers per cycle, and the red curve is just the length of the crack as a function of the number of circles. Frequency was 5 Hertz, dynamic displacement was 2.2 millimeters, peak to peak. Number of cycles between each measurement, each point were 1000 cycles, temperature is room temperature, and we use sinus waveform. And just, okay, it's just simple and really typical for this compound. The crack growth rate decrease with the number of the cycle, and of course the length increase. You have here the comparison between the curve between the crack rate, nanometers per cycle, as a function of the tearing energy. So it's quite simple because, as expected, crack growth rate increase with G. It's quite normal, and the rate versus the energy follow theoretically a power law. You have the coefficient of this law just indicated here. What about the frequency effect? Let's see the understanding of the effect of the frequency on the crack growth rate. First observation, we have a very low effect of frequency on the tearing energy, G. Here you have 3 curves, 3 different colors, 3 different frequency, 1 Hertz in red, 10 Hertz in blue, and 95 Hertz in green. The curve is really close for the same condition, so very low effect frequency on G. However, what about the crack growth rate? Of course, crack growth decrease when frequency increase for the same number of cycles. Why? Because at low frequency, the strain is applied at its maximum amplitude during a longer time for a single cycle. So for one cycle, it's quite important to understand this. For just one single cycle, the crack propagates more. But in relative time, of course, your length of the crack is much more higher at high frequency than low frequency. But for one single, it's not the same conclusion. What about temperature effect? The understanding of the effect of temperature of crack growth system, same observation, G as a function of the deformation. Once again, you can find a very low effect of temperature on G, the tearing energy, but crack growth rate increase with temperature. At high temperature, rubber begin to lose a part of its mechanical properties, and finally the crack propagates more easily. So three different temperatures are shown here: -10 degrees, room temperature, and 100 degrees. And finally, I would like to introduce this curve. Actually, this is the crack growth rate as a function of number of cycle at 100 degrees. And we can find that the crack growth increase over cycle because we notice a thermal degradation of the materials. And for sure, the crack propagates more easily, as you can see at different energy, 1000 and 2000, according to a number of cycles. As a conclusion, test was performed on rubber materials, and tests and results have shown that at low temperature, crack growth rate reach a constant value. The rate versus the energy follow a power law. The crack growth per cycle is important for low frequency, and the crack growth rate increase with temperature, and of course at high temperature, thermal degradation leads to a faster crack growth. Some insights, understanding the waveform effect on the crack growth could be interesting. Studying the correlation between the modulus, tangent delta, and crack growth rate could be interesting also. And studying the crack growth rate among different rubber compounds, of course. Metravib proposed some system with advanced testing capability and match accuracy, extended productivity with multiple cracks followed in one single test. We can automate, this system is fully automated with crack growth, and this is a cost-effective testing solution, and crack growth system can be implemented on any Metravib DMA Plus model, DMA Plus series. Just to focus on the instrument, high performance DMA Plus 300, 1000 and 2000. We propose high frequency capability up to 1 kHz with fatigue testing capability. They are all upgradable models, and we can add a robot for fully automation in order to increase productivity of tests in an industrial way. Thank you very much. If you want to keep in touch, you can contact me directly, or Mathieu, our expert guy, or directly through our website, as you can see just here.
So thank you, Brice, for your nice presentation. It's very interesting to see how with DMA we can perform and analyze all the properties that we have also been seeing during the course that are key for elastomeric materials. So we have been practicing and performing, for example, with the DMA plus 300 that we have here in the article. We have been doing this rapid test that you mentioned to capture the mullins, the pain. As in other talks, we have been also seeing, for example, the talk from Cap, Joseba, which could be key for modeling and for prediction. And this, the other option also for going up to 1 kHz, which is key also for the new requirements, NVH. And also it's interesting to have this opportunity, for example, in the machine we have this DMA 300 to add this fatigue testing capabilities, crack growth testing, because as we have been seeing also in the other talk in Endurica, for the simulation, it's key. And also in terms of sustainability, because we see that these tests are shortest, so we reduce time and cost also. So we increase the sustainability.
I fully agree with you.
Okay, so in my case, after we have a question in the chat, but before I would like to ask you, so you have mentioned that this option can be implemented in other Metravib, and do you give the option to perform demonstration. So demonstration testing is possible?
Yeah, that's a good question. Yes, actually, we have a laboratory in France located near Lyon, and of course, we propose our customers some demonstration testing. We have the whole range of instruments located in Lyon, and especially the new cargo system. So if you want to test or to have a demonstration about the capability of the system, it's a possibility to send us our sample, for instance, and Mathieu or Laurent, our both expert guy, can perform some demonstration testing. They write a report, a testing report, and we can have a short meeting if you want to discuss the results. No problem.
Perfect. So now we can go with the question that we have in the chat. So Olat is asking, okay, hi, Brice, thank you for your presentation. And I would like to ask you about the advantage between characterizing, you mentioned 4 cracks or 2 cracks.
Yeah.
So which is the advantage of?
Okay, that's a good question. Actually, if you measure 2 cracks instead of measure 4 cracks instead of 2 cracks, you increase your repeatability and your productivity of results. It's just about statistic results. We can compare 4 cracks with 4 different specimens because we use the same batch, the same rubber, the same elastomers. So you can increase easily the number of crack growth results in the same test. So it's just a matter about statistics.
Interesting. So you increase the efficiency of the...
Exactly. Yeah, you are more productive.
Perfect. So I don't know if you have any other questions from the speakers. If not, we can now. We will need to change, and because Brice needs to.
Yes.
He needs to leave. So José Javier Segurola is going to join.
Thank you very much, and we keep in touch. Of course, we remain available for any further questions. Thank you very much, Leartica. Thank you, SAT.
Thank you, Brice.
Right again. So we have now the last presentation that is coming from Leartica. So my colleague Iseti will do the last presentation. So just some few words about Iseti. Well, she's a researcher within the sustainable transport area in Leartica, PhD on material science and technology by the University of the Basque Country in 2022. Before, she carried out physics and electronics engineering bachelor degree and new material master's degree in the University of the Basque Country also. During the last 5 years, she has focused on the characterization, modeling and simulation of elastomic materials and components, mainly for the automotive sector. Her research activities are mainly focused on the study of dynamic mechanical behavior and durability of elastomer materials, rubber and thermoplastic elastomers, not only in terms of characterization, but also in modeling or digitalization strategies. So, Iseti, this is your turn.
So I will share my presentation. Okay. Where's it? Here. Okay. Full screen. Okay. So, first of all, good morning to everyone, and thank you, José Javier, for your kind introduction. So today, my idea is to present some results that we have obtained in 2 particular research projects that show somehow the potential of understanding the dynamic mechanical behavior of elastomeric materials to optimize the performance properties of elastomers in material level, but also on the product level. So optimize the performances of products that are used in the sustainable transport or transport sector. Okay, so this is an outline of what I'm going to present today. So first, I will very quickly introduce Leartica's sustainable transport specialization areas. Then I would talk very briefly also about some the transport industry challenges that are appearing related with elastomeric materials. And then I will go more in detail through the two case studies or research projects that I will present. So the first one is going to be related on how to improve the structural vibration damping capability of high stiffness product or materials by means of the incorporation of TPE materials. And then I will also introduce some research activities that we are performing in terms of how to personalize or tune the vibration damping capabilities of TPE materials, which are a special class of TPE materials that are obtained by blending thermoplastic with rubbers. And of course, at the end, I will summarize a bit and I will talk about some perspectives. Okay. So in the sustainable transport area that we have in Le Artiker, we perform research and development activities in order to transfer to the transport sector and industry the most advanced expertise and knowledge related with the design and the development of lightweight, reliable and silent polymeric structures, and of course, how to digitalize their behavior by means of advanced material modeling and techniques. Inside this sustainable transport area, we research in different fields of applications, so mainly in three kinds of polymeric materials, which are sheet molding compounds, thermoplastic composites, and elastomeric materials. But regarding elastomers, the activities that we perform, all the research activities that we perform are focused to advance the use of elastomers in the demanding dynamic applications, mainly focused with the new mobility issues and problems. And for that, we work and research in what we call properties-driven strategies. So strategies that are aware of the process structure properties relationship in elastomeric materials. And with the development of these kind of strategies, we are targeting the improvement in terms of the efficiency and carbon footprint of the material and product development workflow. So we are targeting reduction in energy consumption, cost, and time to market. That's why the name sustainable transport is for that, to apply this knowledge in elastomers for sustainability, impacting sustainability. Okay, so in terms of the challenges that are appearing in the transport industry related with elastomers, so as we all know, elastomeric components that are used for noise and vibration insulation in the transport industry. So for example, bushings, engine mounts that are used in the transport industry are traditionally made of thermoset rubbers, but there are appearing new needs, new legislations, we are more care now with the sustainability, as we have also mentioned in other talks, the life cycle analysis, and there are appearing also new requirements related with electrical mobility, so high frequency requirements, new NVH requirements that are pushing the introduction of TPEs for noise and vibration control. So a huge number of opportunities arise when looking at the contributions that TPEs can have for such kind of applications. And of course, there is a huge deal of room for research and developments in this area. So the two projects that I will show are related with this, how to introduce TPE materials to overcome all these challenges and how to optimize the behavior of the material and products by means of these strategies that we are working in the article, these properties-driven strategies. So in the first case, as I said, the objective was to investigate passive solutions to improve the noise and vibration, mainly structural dampening, and how to decrease the noise performance of transport industry structural components. So for that, we designed some bimaterial structures, but by combining high stiffness material. In that case, we work with SMC materials, sheet molding compounds, which are very interesting materials in terms of mechanical properties and thermal properties, but they have some issues related with the structural dampening due to the high stiffness of these materials. So in this project, we combined this SMC with a viscoelastic material, in this case, a green viscoelastic material, so a TPE material. So as I mentioned, as SMC has this relatively poor vibration dampening at room temperature mainly, due to the, as we will see later, the high glass transition values of these materials, we combine SMC with TPE for improving or targeting improvements of the vibration dampening at room temperature. So for that, the first thing was to select TPE materials with loss factor values higher than 0.3. As I will explain later, we use loss factor, which is a property that can be captured by DMA, because this factor is related with the dissipation ability or the intrinsic dissipation ability of materials and gives an information of this structural dampening capability of materials. Okay, so as I said, we have selected several materials with these specific properties. We developed some structures. We developed during the project two kinds of free layer damping and sandwich. Today I will show the results related with the free layer. But of course, if you are interested in this kind of results, we are kindly and we can show you also in other presentations. And then for capturing the behavior, we perform some DMA tests to control, as I said, the vibration dampening capability at different temperatures and also at different frequency ranges. So in terms of the material selection, so the TPEs that we used for this study were from Avient, so were supplied by Avient, because Avient has some special grades TPE materials with very good vibration damping capability at room temperature, and also they are formulated to blend different kind of materials. In our case, we were interested in blending capability with a polyester-based SMC, which is reinforced with a glass fiber, and an epoxy-based SMC, which is reinforced with carbon fiber. Okay, so that's why we selected these two Avient TPEs with good vibration damping capability, as we will see later, tan delta higher than 0.3, and good bonding capability with these two specific SMCs. So this is some pictures of the structures that we developed. So on the one hand, we perform some free layer damping structures, which is a very simple structures and which is widely used in the automotive sector, mainly due to the simplicity. And then we also perform some sandwich structures, mainly because in the sandwiches we saw that we have a higher application temperature ranges. But as I said, as in this case we are targeting room temperature and high temperature is not key for this application, we will focus on the free layer damping. Okay, so in that case, the idea is to bond to a stiff layer a viscoelastic layer. And so when this structure will suffer bending mode, the viscoelastic layer is able to dissipate energy and to give to these structures this vibration dampening capability. Okay, so here you can see some dynamic mechanical analysis tests we perform. These are specific for temperature sweep experiments, which are experiments that give a lot of information about the viscoelastic properties of the materials, for example, in terms of material selection for product requirements when the product is under cyclic conditions. So in that case, as I mentioned earlier, and as you can see in the graphs, the SMC materials, which are the UP and E, so unsaturated polyester is the UP and E is the epoxy. So we can see that the stiffness value, it's very high, but the loss factors that we have at room temperature, 30 degrees, it's very low. So high stiffness, but then bad vibration damping capability. But in the other hand, if we compare the TPE performances, viscoelastic properties, we can see how, in this case, the stiffness values are low, but then the loss factor, tan delta, vibration damping capability or dissipation energy that these materials give to the structure, it's very high. If we compare these ambient grade TPE materials, we see that at room temperature, the loss factor is higher than 0.3, which means a very, very good vibration damping capability. And also, in terms of the range, if you take a look to the table, we can see that the range with a loss factor higher than 0.3 with these TPE materials could be very wide. So in the case of the TPE2 material, it's very broad from 2 to 61 degrees. So we can go upper than room temperature. Okay, so what we done, as I said, it's temperature sweep test. We have also, as you can see in the left, we have also performed a room temperature frequency test. But what happens usually is that when performing different DMA tests, frequency, temperature, you get a lot of graphs, and then it's not very easy to compare different materials, different structures for the target that we have in mind. In our case, it's a component that needs to be have at room temperature very good dampen and high stiffness values, because we need to add, or we want to add TPE to improve the vibration dampening, but not to reduce the stiffness or structural part that SMC gives to this kind of applications. So for that, as we can see, they are very interesting to compare the loss factor with the storage modulus. These kind of graphs are known as wicket plots and give a lot of information when comparing different materials in terms of the target or goal viscoelastic properties. In that case, as I mentioned, we want, or the ideal range for the component is high modulus and high damping. So in that case, for example, if we compare the different structures with different thicknesses, for example, the free layer epoxy with 1 millimeter, if we compare it with free layer epoxy 0.5, we can see that with increasing the thickness of the TPE layer, the modulus is decreased and we have a higher dependency with the frequency and temperature. So it's more dependent on the frequency and temperature, so more viscoelastic. If this is something that we do not have, we want to, if we want to have a material or a structure that is more stable with frequency and with temperature, then we have a best compromise between all of them when adding 0.5 to the free layer or epoxy-based SMC material. Because as we can see in the graph, in this case, we have high stiffness values, more or less similar to the unsaturated polyester SMC, and with good damping values up to 0.2. So we have moved more or less from 0.0 very low damping values up to 0.2 by adding 0.5 millimeter TPE to the structures. And even more interesting is that in that case, we have a very low dependency with frequency and temperature. It's very stable with the frequency and temperature. So the general conclusions that we obtained in this study is that these SMC TPE material combinations are able to improve the damping properties of SMCs, but also maintaining the stiffness of the SMC structures. So we are in the range of the stiffness values of, for example, adding to a epoxy-based 0.5 millimeter TPE in the range of an unsaturated polyester in the case of epoxy. And we think that based on the results we obtained, the addition of this 0.5 millimeter TPE layer is the one that shows the best balance or compromise between good damping properties and stiffness reduction. Okay, so now let's jump to the second case study or research project. This is related more with the strategy that I was talking at the beginning, this properties-driven strategy, so how the process can influence the microstructure of the materials and how with this we can tune or personalize the final properties of material and also components. So in that case, what we did was investigate the anisotropic microstructure and properties of injection molded thick-walled TPBs. Why thick? Yeah, because as we mentioned, we want to replace elastomeric materials by TPEs in anti-vibration components. So bushing, top mounts, these kind of components have very thick wall thicknesses. So the interesting here is to analyze the effect of this also, because then at the end, we would like to close the loop and be able to predict the properties also at the product level. Okay, so as I said, usually this vibration dampening is achieved by using elastomer-based components that have tailored geometry and tailored static and dynamic mechanical properties. So for that, the interesting thing would be to select elastomers with personalized or tunable dynamic stiffness, static stiffness, and also hysteresis. Hysteresis, why hysteresis? Because the hysteretic heating is also related with the fatigue or long-term dynamic mechanical behavior of this kind of material and products. So as I said, in this kind of materials, we have two phases. So we have a thermoplastic and a rubber. So we need to control the microstructure because this is going to influence then the final properties, which are these very non-linear, static, and dynamic mechanical behavior that you usually need to control also in product level. So in that case, for this specific research project, we used 3 different PP EPDM Santopren TPBs with different short hardness, because it's interesting also to analyze the effect of the hardness on their final properties. Usually for anti-vibration components, we are targeting short values of 60, so soft materials, but of course it's interesting to analyze other ranges for other kind of applications. So for the processing or for the generation of the coupons then for testing, we have used this plate that you can see, sorry, in the slide. So we injected the plates by using an Engel vertical injection molding machine that we have here at LearPicker, and the processing information that we have used is the one that is specified in the material datasheet. So the one that we will use then when injecting or processing these materials at component level. And as you can see in the figure, we consider 2 regions. So we consider the middle of the plate and also the end of the plate in order to also analyze the effect of the flow during when going through the mold, okay? And then we cut the testings longitudinal and transverse because as I mentioned, the objective is to analyze the anisotropic behavior of this kind of materials. So now I will present the key findings that we obtained in this study. So on the one hand, one key performance that is very, very important when we want to replace a rubbery material with a TPB material is the elasticity or permanent deformation, because these TPB materials, they have a thermoplastic as a matrix. In that case, we have a polypropylene as a matrix. So we'll have a plastic deformation, but for anti-vibration components, we want to have a good elasticity, so a low permanent deformation values, okay? So it was very interesting to find how in the low hardness values, which are the ones that are more interesting also for the final application for these anti-vibration components, such as bushing or toe mounts, for example, how in these hardness values, we obtain improvements in the elastic recovery in this case, in the transverse direction. So that means that if we are able to control the process and the microstructure that we obtain in the injection molding process, hopefully we will be able to obtain products or materials with better elastic recovery ability, okay? Then, of course, for this kind of components, it's also very important to control the effect of the frequency on them. So for that, as in the other case, we have performed some frequency sweep experiments and then analyze the relationship we have between the storage and loss modulus, okay? Because the storage modulus, or the G prime, gives information about the energy that is stored in the material, And so the tendency that we'll have to demonstrate an elastic behavior, and the loss modulus, or E double prime, is related with the energy dissipation capability, and so the tendency to demonstrate this damping or vibration dampening behavior. So it was also here very interesting to find that at low shore hardnesses, in this shore A60, we are able to somehow customize the dynamic mechanical properties of these materials. That means that if in the final performances we are achieving, or we would like to have different ratios between the static and dynamic stiffnesses, different loss factor or dampening capabilities, we should be able, if we are able to control the process, if we are able to control the final microstructure that we have in these materials, we should be able to optimize and also customize the final properties that we will obtain in material and product levels. So the main conclusions in this second project was that, as we saw, with decreasing the hardness, the material is more anisotropic. So that means that in these shore A60 materials, we are able to tune their performances, not only static, but also dynamic mechanical properties. And so we think that there is a room here to research and to improve the performances of TPV materials, improve their elasticity in terms of low values of permanent deformation, and customize or personalize the dynamic mechanical characteristics by adjusting this flow-induced anisotropy. So somehow controlling the processing and the microstructure. So as a summary or perspective, I would say that in the case of the how to improve the structural dampening of structural components by adding TPE, so these passive vibration dampening strategies with TPEs, I think that this study opens new prospects to design lightweight, multifunctional components for modern transport applications, and particularly for applications that are facing both damping or resonance issues and challenging mechanical requirements, such as, for example, car grounds, car roof, or aircraft wheel components. And in terms of the TPVs and the study related with their anisotropic behavior, this study, I think, demonstrates the advantage of introducing this anisotropic behavior of TPE blends in the TPV-based anti-vibration component design and optimization strategy. So be aware of the microstructure and how can we use this to optimize the final properties of this kind of components and materials. So I have finished. This was a bit what my intention today to present, to show you. So now, thank you all, and I'm open for the questions.
Thank you very much for your nice presentation, and thanks for showing which is the relationship between formulation, material processing, characterization, and of course everything it's influencing the design of a new part. You know? So well, now we can open a discussion time. I don't know if someone in the audience have any question. Okay, so well, we have one question in the YouTube channel. So Kepa is saying, hello Isete, thanks for the presentation. And he's asking about which is the behavior of those bimaterial samples in low temperature.
Mm-hmm. So we can take a look to the graphs I showed, because probably that was very fast. So I think that with low temperature, I think could be below room temperature. So in that case, we can see, for example, that TPE1 material, okay? So depends on the material selection. We can see that, for example, this specific TPE has the loss factor peak, which is, I didn't mention, which is related with the glass transition temperature. So the dissipation capability of the materials its maximum at the glass transition. So in that case, the tan delta peak value of these materials is at -1. So that means that with these materials, we could or we would be able to have structures with good vibration damping capability because the peak is at -1. But of course, this depends on the material selection and the final targets we obtain. Another way to see how these materials will behave at low temperatures is by using the time temperature equivalences. So it's a modeling strategy we have been also explaining at the course. And this means that the behavior they have at high frequency is somehow related with the low temperature properties that we will obtain with these materials. So by controlling this also, and we can see how, in this case, for example, different structures have different curves or shape at frequency. So there are some materials or some structures, for example, this one, the free layer E05, that has a decreasing tendency in the loss factor with the frequency. This means that at low temperatures, this structure will have lower damping capability. But then there are another structures, for example, the one related with unsaturated polyester, that have an increasing tendency with frequency, which means that they will probably behave better at low temperatures. So there are ways also to analyze and to see the effect of the temperature frequency by means of this short test in DMA.
Mm-hmm. Okay, thanks. Any other question? Rest of the speaker have any question? Okay, so well, if there's no any more question, we can just finish this expert talks event. Well, first I would like to thank the speakers, Elias, Brice, Will, Joseba, and Iseti for those nice presentations. And well, we can make some kind of summary. You know? Well, the first we have Joseba explaining well, how important are dynamic properties in the designing of a transport or a train, not only for the comfort, but also for the safety point of view. Then Elias explained us which was the weight range of sustainable materials that ABN has developed, taking into account the bio-based materials and also the recycled content in different thermoplastic elastomers. Will was explaining importance of the durability in the designing of new products and how specific or how important it is to have a good simulation tool in order to facilitate those simulations. And then Brice was also explaining which important is a good characterization of the materials in order to take decisions in the product development. And finally, the last presentation of Iseti was connecting like a different key parameters, material formulation, material characterization, and how important it's the process, because the characteristics of the materials will depend on the processing, and then of course the modeling of those materials. So I also like to thank the audience for being connected, and well, I hope to see you again during the next DYNAeLAST program. It has been the first edition, but well, the idea is to go on during the next years and trying to do it presentially. That's also one of our options. So well, that's it. Do you have something to add?
Yeah, I will say that for us, this is an event where we can all meet, share the different issues, share our knowledges, and as we have also in the webpage, somehow advance and introduce the new developments we have in order to advance the new developments in terms of elastomers, dynamic properties. And for us at the end, it's a networking opportunity, or we would like to have this event in order to have all of the partners that we are involved in the transport sector. We work with elastomeric materials. We suffer the non-linear behaviors and the conditions at the component level that need to suffer this kind of products. So have this event in order to have this networking opportunity to share the different issues we have, the different problems, and of course share our knowledges, scientific issues, more industrial issues. So that's the main idea or the main goal for us.
Mm-hmm. Okay, thanks, Vicente, and well, have a nice day and see you. I hope see you soon
Next year,
and
yeah.
again next year.
Sure.
Okay.
Bye bye. Thank you all.
Bye.
Yeah.
Thanks
Thank
all.
you very much.
Thank you.
Bye.
Bye.
Thank you.
Thank you.
Bye.